Gravity, the journey to the edge of falling. What if I told you that you're falling right now? Not falling down, but falling through the universe at thousands of kilometers per hour. We think of falling as a clumsy mistake, a brief, unwanted trip that ends with a painful, sudden stop. It's an accident, an interruption, but the secret to everything, from the moon in our sky to the planet beneath our feet, is that this idea is completely wrong. Falling is the default. It's the natural state of the cosmos. And the most beautiful dance in the universe is the art of falling forever, without ever hitting the ground. This is the story of gravity, but not the one you think you know. This is the journey to the edge of falling. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The misconception of the fall. First, let's talk about what falling feels like. It's a primal fear, a total loss of control. The moment your feet leave solid ground, your stomach lurches. For a brief, terrifying instant, you are weightless. There's only the rush of air and the rapidly approaching ground. The fall itself is rarely the problem. It's the asterisk landing we're afraid of. That abrupt, unceremonious reunion with the surface of the earth. Our entire lives are built around avoiding this. We build sturdy foundations, we watch our step, we hold on to railings. In our language and our stories, a fall is almost always negative. We talk about the fall of an empire, a fall from grace, or how things fall apart. To fall is to fail, to lose stability, to descend from order into chaos. But what if that perception is the real illusion? What if the state we call normal, standing firm on solid ground, is the artificial one? What if that solidness under your feet isn't a state of rest, but a state of constant, forceful interruption? To understand this, we have to rewind our thinking and go back to a time when the rules for the heavens and the rules for the earth were considered two completely separate things. A time before one simple thought about an apple changed everything. Before the 17th century, the common wisdom, inherited from philosophers like Aristotle, was that the cosmos was divided. There was the earthly realm, where things were imperfect and always moved towards their proper place. A rock, being of the earth, wanted to fall to the earth. Smoke, being of the air, wanted to rise to the sky. And then there was the heavenly realm, where the sun, moon, and stars moved in perfect, eternal circles, made of a divine substance called ether. The rules down here were not the rules up there. This was accepted for nearly 2,000 years. The idea that a single law could govern both the clumsy fall of a piece of fruit and the majestic path of the moon was not just unproven, it was almost unthinkable. It would take a uniquely brilliant mind to see the connection and unify the heavens and the earth under one universal idea. It would take Isaac Newton. Newton's universal secret. The story is a classic, maybe more legend than fact, but its core idea is what truly matters. Isaac Newton, sitting under a tree, sees an apple fall. But where others saw just an apple, Newton saw a question. He didn't just wonder why it fell. He asked, how far does that why go? Did the force that pulled the apple to the ground stop at the top of the tree? Or at the tops of the mountains? Or did it, maybe, reach all the way to the moon? This was a radical leap of genius. Newton proposed that the very same force, which he named gravity, was responsible for both. He suggested that every particle of matter in the universe attracts every other particle. This pull depends on two things: how much stuff, or mass, the objects have, and how far apart they are. More mass means a stronger pull. More distance means a weaker pull, diminishing with the square of the distance. This was his law of universal gravitation, and it was a revolution. It meant the moon wasn't held in the sky by some divine, unknowable power. It was being pulled by the earth. The planets weren't circling the sun because it was their heavenly duty. They were being pulled by the sun's immense gravity. The universe, from a grain of sand to a giant star, was all playing by the same rules. There was no longer an up there and a down here. It was all one cosmos, bound by this invisible, ever-present force. But this led to a new, glaring question. If the Earth is constantly pulling on the moon, why doesn't the moon crash into us? If the sun is pulling on the Earth, why don't we just plunge into its fiery heart? The answer lies in another of Newton's brilliant thought experiments, an idea that reveals the true nature of falling and the secret to the most graceful dance in the cosmos: the orbit. Imagine a cannon on top of a mountain so tall it pokes above the atmosphere, so there's no air resistance. Now, you fire it. A small amount of gunpowder, and the cannonball travels a short way, curves down, and hits the ground. It falls. Now, add more gunpowder. The cannonball goes much faster and much farther before it, too, curves down and hits the Earth. It's still falling, just taking a longer trip. This is where Newton's insight changes everything. What if, he wondered, you could fire that cannonball with just the right amount of incredible speed? As the cannonball starts to fall, its huge forward velocity carries it over the horizon. The Earth is a sphere, it curves away. So, as the cannonball falls, the ground beneath it is also curving away. If the speed is perfect, the curve of the cannonball's fall will exactly match the curve of the Earth. The cannonball is still being pulled by gravity. It's in a constant state of falling toward the planet's center. But it never gets any closer. It perpetually misses the ground. It is falling, forever, in a circle around the Earth. That is an orbit. An orbit isn't the absence of gravity. It is the victory of sideways motion. It's the art of falling so fast that you continuously miss the thing you're falling toward. This isn't just a clever idea. It's reality for every satellite, for the moon, and for our own planet. Take the International Space Station, the ISS. It orbits at an average altitude of about 408 kilometers, traveling at a staggering 27,600 kilometers per hour. That's about 7.7 kilometers every single second. At that height, Earth's gravity is still about 90% as strong as it is on the surface. The ISS, and everything in it, is constantly being pulled toward Earth. It is in a perpetual state of free fall. This is the secret to the weightlessness astronauts feel. They aren't floating because they've escaped gravity. They're floating because they, the station, and everything inside are all falling together. It's the exact same feeling you get for a split second at the top of a roller coaster hill, or when an elevator starts to descend quickly. In that moment, you are falling, and you feel weightless. Astronauts on the ISS live in that moment, continuously. They are falling around the Earth. Now, let's zoom out to our moon. It's the same principle, just on a grander scale. The moon is an average of 384,400 kilometers away. Even at that immense distance, Earth's gravity pulls on it, causing it to accelerate toward us. And just like the cannonball and the ISS, the moon has a huge sideways velocity, traveling at an average of 3,700 kilometers per hour. This speed is a cosmic inheritance from its violent formation billions of years ago. It's the perfect speed to ensure that as it falls toward the Earth, it consistently misses. The moon is falling, right now. It just never lands. And what about us? The Earth itself? We are on a much larger cannonball. Our planet is hurtling through space, orbiting the Sun at an average speed of about 107,000 kilometers per hour, or nearly 30 kilometers every single second. We are relentlessly pulled by the Sun's colossal gravity. We are, all of us, every moment of our lives, on a planet in a constant, high-speed free fall around a star. The only thing preventing a fiery end is our planet's tremendous sideways momentum, keeping us in that perfect, life-sustaining orbit. So falling isn't an accident. It isn't a clumsy mistake. It's the fundamental operating principle of the solar system. From the smallest moon to the largest planet, everything is constantly falling. The stability we see in the night sky isn't a static calm. It's a dynamic, high-stakes equilibrium, a cosmic ballet where everyone is falling, and everyone is missing. Newton's laws were a triumph. They gave us the tools to predict the planet's motions, understand the tides, and send probes to the far reaches of our solar system. But even Newton was troubled by a deep mystery in his own theory. How did gravity work? How could the sun, millions of kilometers away, reach out across empty space with no physical connection and pull on the Earth? This action at a distance, as he called it, seemed magical, and he famously had no explanation for it. For over 200 years, that question hung in the air. Gravity was a force that just was. It took another once-in-a-generation mind to look at the problem from a completely new angle and reveal a truth about the universe even stranger and more beautiful than Newton could have imagined. It would take Albert Einstein. The deeper reality of the fall. At the turn of the 20th century, a young patent clerk in Bern, Switzerland, was wrestling with the nature of light and motion. Albert Einstein's 1905 theory of special relativity had already fused space and time into a single fabric, spacetime. But Newton's gravity didn't fit. Newton's force was instantaneous, while Einstein had shown that nothing, not even information, could travel faster than light. Something had to give. Einstein's breakthrough began with what he later called his happiest thought. It was a simple idea with profound consequences. He imagined a man falling from a roof. As long as the man is in free fall, he doesn't feel his own weight. If he took objects from his pocket, they would float beside him, seemingly weightless. In his immediate surroundings, the effects of gravity would vanish. Einstein refined this into another thought experiment, the elevator. Imagine you wake up in a sealed room with no windows. You drop a ball, and it falls to the floor, accelerating at 9.8 meters per second squared, just as it would on Earth. The natural conclusion? You're in a stationary elevator on Earth. But Einstein proposed an alternative. What if you're actually in deep space, far from any gravity, and the elevator is being pulled up by a rocket, accelerating at that exact same rate? From inside the box, how could you tell the difference? The ball would seem to fall with the same acceleration. Your feet would feel pressed to the floor by the same force you call weight. No experiment you could perform inside that room would give a different result. Einstein concluded that these two scenarios, being in a gravitational field and being in an accelerated frame of reference, are not just similar, they are asterisk equivalent. Now, flip the scenario. The elevator is on Earth, but its cable just snapped. It's in free fall. Inside, you and the ball you're holding fall at the same rate. If you let it go, the ball simply floats in front of you. You feel completely weightless, just like you would in an elevator floating motionless in deep space. This was the key. Free fall isn't just a type of motion within a gravitational field. Free fall is the state where the effects of gravity disappear. It is the natural, unforced, straight-line path through the universe. So if falling is the natural state, what is the weight we feel right now? It's not gravity pulling you down. It is the ground pushing up, preventing you from following your natural, free-falling path. Your weight is the measure of the floor's resistance to your fall. You are being constantly accelerated upwards by the planet's surface, and that is what you feel. This led Einstein to his most profound revelation. If gravity wasn't a force, what was it? He proposed that gravity is a consequence of the shape of the universe itself. Mass and energy, he argued, literally bend and warp the fabric of spacetime. The classic analogy is a bowling ball on a stretched rubber sheet. The ball creates a deep dent. Now, if you roll a small marble nearby, it doesn't travel in a straight line. It follows the curve in the sheet created by the bowling ball. With just the right speed, it will circle the bowling ball in an orbit. Crucially, there's no mysterious force pulling the marble. The marble is simply following the straightest possible path through the curved surface. The surface itself directs its motion. According to Einstein's theory of general relativity, this is gravity. The Sun isn't pulling the Earth. The Sun is so massive it creates a huge dent in four-dimensional spacetime. The Earth is simply following the straightest possible path, a geodesic, through that curved spacetime. That path, from our perspective, looks like an orbit. Gravity is not a force. Gravity is geometry. An apple falling from a tree is just following its geodesic through spacetime curved by Earth's mass. A satellite, the Moon, and the Earth are all just following their own geodesics. An orbit is a straight line through a curved universe. This was proven in the most dramatic way possible. On August 2, 1971, during the Apollo 15 mission, Commander David Scott stood on the Moon. In one hand, he held a geological hammer, and in the other, a falcon feather. On Earth, air resistance would make the feather flutter down. But on the airless surface of the Moon, there was only gravity. He dropped them both. In one of history's most iconic science videos, the hammer and the feather fell together and hit the lunar dust at the exact same instant. It was a beautiful demonstration of what Galileo had first proposed and Einstein's theory required. In a vacuum, all objects fall at the same rate, because they are all following the exact same curvature of spacetime. This journey from a clumsy trip to the fabric of the cosmos is one of the most amazing stories in science. It changes how you see everything. We think asking big questions about the universe is one of the best things you can do with your mind. If you agree, subscribe and hit the notification bell to join us on our next exploration. And if there's a cosmic mystery you want to see unraveled, let us know in the comments. Your question might just be our next adventure. Conclusion: we began with a simple question. What if falling isn't an accident? Our journey took us from the ground beneath our feet to the edge of the solar system and to the very fabric of reality. We saw through Newton's eyes that falling is a universal law connecting an apple to the Moon. We learned that an orbit isn't about escaping gravity, but mastering it, the art of moving sideways so fast that you perpetually miss the ground in an endless, graceful fall. We learned that the International Space Station, the Moon, and even our own Earth are all, right now, in a state of constant free fall. Then, with Einstein as our guide, our understanding went even deeper. We found that falling is the most natural state of being. It's the effortless path objects take through a cosmos shaped by mass and energy. The solid ground we stand on isn't a state of rest. It's a constant, forceful interruption of our natural journey. The weight we feel isn't the pull of gravity, but the push of the world, holding us back from our true path. Gravity is not a force that pulls. It is a curvature that guides. Falling is not a descent into chaos. It is a movement that follows the very contours of spacetime itself. So the next time you stumble, or drop something, or just feel the solid certainty of the floor beneath you, remember what's really happening. You are not a static being on a stationary rock. You are a passenger on a planet, hurtling through the cosmos at unimaginable speed, in a constant, silent, beautiful fall around a star. The feeling of being still is the illusion. The endless journey, the graceful dance on the edge of falling. That is the profound reality we all share. The silent force warping your reality right now. Take a look at the clock on the wall. Now, look at the space between you and that wall. Right now, a silent, invisible force is warping that space and slowing down that clock. You can't feel it, but it's the most powerful sculptor in the entire cosmos, and in the next few minutes, you're going to understand exactly what it is. No, this isn't science fiction. This is a fundamental property of the universe acting on your body, on the chair you're sitting in, and on the air you're breathing, all without making a sound. We're living our lives on a stage where the floor itself is constantly bending and twisting, dictating every move we make. We think of empty space as, well, nothing. A void just waiting to be filled. But the truth is so much weirder and more profound. That emptiness is an active, dynamic landscape, a fabric that can be stretched, compressed, and warped. We're about to peel back a layer of reality you never knew was there. And by the end of this, your whole perception of stillness, of motion, of empty space, and even of time itself is going to be permanently altered. You'll understand that the most basic experience you have, the feeling of being held to the earth, isn't what you think it is. It's an illusion, a beautiful trick played on our senses by the silent force that shapes everything. The illusion of stillness and the Newtonian ghost. Let's start with something that feels solid and real. The ground under your feet or the chair holding you up. It feels stable, unmoving. But inside that stillness, there's a constant, raging battle. To get it, we need to jump back in time to the 17th century, to a world lit by gas lamps and ruled by the ideas of one man, Sir Isaac Newton. You know the story. Newton sees an apple fall, he looks up at the moon, and in a stroke of genius, he connects them. He realized the same force pulling the apple down was also holding the moon in its orbit around the Earth. He called it gravity, and he gave us a neat mathematical law to describe it, the law of universal gravitation. This law was a triumph. It explains that the gravitational force between two objects depends on their mass and gets weaker the farther apart they are. It's like an invisible tether that every object has on every other object. You're pulling on the Earth, and the Earth is pulling on you. The sun pulls on the Earth, keeping us in our yearly dance, and the Earth pulls right back. For over 200 years, Newton's idea was king. It explained planetary orbits, the arc of a cannonball, and the fall of an apple with stunning precision. We built our world on it. But there was a ghost in the machine that bothered even Newton himself. He called it action at a distance. Think about it. How does the sun, 93 million miles away, tell the Earth to stay in orbit? How does it pull on us across a vast, cold vacuum, instantly? Does it send a message? In a letter, Newton said the idea of gravity acting over a distance with nothing to carry it was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He knew how to calculate gravity, but he had no idea what it was. It was just a magical, invisible string. Now, let's go back to our quiet room. A book is sitting on a table. According to Newton, the massive Earth is pulling that book down with a constant force. The only reason it doesn't fall is because the table is pushing back with an equal and opposite force. The book is in a perfect balance, a silent tug of war. The wood fibers in the table are under constant strain, fighting a battle against an invisible giant. This is the Newtonian world. Everything that's just standing still is actually in the middle of a perpetual, silent fight. This picture makes a lot of sense. We feel the pull of gravity every day. But that nagging question, Newton's ghost, remained. What is this invisible string? The answer wouldn't come for another 2 centuries, and when it did, it didn't just tweak Newton's idea. It shattered it completely. And to find that answer, we have to leave the world of forces behind and enter the world of Albert Einstein. The great revelation, Einstein's beautiful idea. The beginning of the end for a 200-year-old pillar of science didn't happen in some grand lab. It happened in the mind of a young patent clerk in Bern, Switzerland. In 1907, Albert Einstein was thinking about his theory of special relativity, which had linked space and time. But he knew it was missing something big, gravity. The breakthrough came from what he later called his happiest thought. He imagined a man falling from a building. As this person falls, Einstein realized they wouldn't feel their own weight. If they dropped something from their pocket, it would just float there beside them. In their little bubble of existence, gravity would seem to have vanished. They'd be perfectly weightless. This one simple idea sparked a revolution. Einstein then took it a step further with one of the most famous thought experiments ever, the elevator. Imagine you wake up in a sealed elevator with no windows. You drop a ball, and it hits the floor. You feel your feet pressed firmly down. What do you conclude? Easy. You're on Earth, and gravity is pulling you and the ball down. But now, what if you were in that same elevator out in deep space, far from any planet? A rocket strapped to the top fires, accelerating you upwards at 9.8 meters per second squared, the same as Earth's gravity. What would you feel? Your feet would be pressed to the floor with the exact same force. If you dropped a ball, the floor would rush up to meet it, creating the asterisk illusion that the ball was falling. From inside the room, there is absolutely no experiment you could do to tell the difference between sitting still on Earth or accelerating through space. This is the equivalence principle, and it's the heart of Einstein's new theory. It says that, locally, gravity and acceleration are indistinguishable. This was a huge clue. If acceleration can perfectly mimic gravity, then maybe gravity isn't a force at all. This led Einstein to a mind-blowing conclusion. Objects aren't being pulled around by a mysterious force. They are just following the straightest possible path they can through the universe. So why do planets orbit the sun? Why does an apple fall? Because the universe itself isn't flat. It's curved. To get this, you have to upgrade your view of reality. We used to think of 3 dimensions of space, length, width, height, and time as a separate, universal metronome. But Einstein had already shown that space and time are woven together into a single, 4-dimensional fabric called asterisk spacetime. This is the stage where everything in the universe happens. And here's Einstein's masterpiece, general relativity. Mass and energy don't just sit in spacetime. Mass and energy tell spacetime how to curve. And in turn, the curvature of spacetime tells matter and energy how to move. The classic analogy is a rubber sheet. Put a bowling ball in the middle, and it creates a deep well. Now roll a marble nearby. It won't travel in a straight line. It will follow the curve made by the bowling ball, spiraling inwards. An outsider might say the marble is being pulled by the bowling ball. But from the marble's point of view, it's just going straight on a curved surface. That path is called a geodesic. This is Einstein's gravity. The sun is a massive bowling ball that creates a huge dent in spacetime. The Earth, a little marble, isn't being pulled by an invisible string. It's just following its geodesic, the straightest path possible, through the curved spacetime the sun creates. The result of that straight path in a curved geometry is an orbit. Now let's go back to our book on the table one last time. There is no force pulling it down. The mass of the Earth has warped spacetime, creating a downward slope, right where the book is. The book wants to follow its natural, straight path down that slope. It wants to free fall. So what's the table doing? It's not fighting a downward pull. The table is actively getting in the way. It's pushing the book up, stopping it from following the natural path it wants to take through curved spacetime. So that feeling of weight you have right now? That's not the pull of gravity. It's the atoms in the floor pushing your atoms up, constantly accelerating you just to keep you standing still. You're fighting the very shape of reality. That's the silent force. It isn't a pull. It's the push of the world against the geometry of the cosmos. The proof: seeing the invisible. This idea, that reality is a curved, 4D landscape, is one of the most beautiful in science. But science demands proof. If space is really bent, we ought to be able to see it. And if time is part of this fabric, it should be bendy, too. Einstein's theory made some wild predictions, and it would take some wild evidence to prove them. Part A. Warping space. Einstein published his theory in 1915, and his most testable prediction was that if mass curves spacetime, then even massless light should get its path bent when it passes a huge object. He calculated that starlight passing by the edge of the sun should be deflected by a tiny but measurable 1.75 arcseconds. That's a ridiculously small angle, like the size of a dime seen from 2 miles away. The problem, of course, is the sun is bright. You can't see stars next to it. The only way to test this was during a total solar eclipse, when the moon would perfectly block the sun's light. Enter English astronomer Sir Arthur Eddington. In 1919, just after World War I, he led 2 expeditions, one to Príncipe, an island off Africa, and another to Sobral, Brazil, to photograph an eclipse. The mission: take pictures of the stars around the blacked-out sun and compare them to pictures of the same stars taken months earlier. If Einstein was right, the stars closest to the sun's edge would look like they had moved. The expeditions were a mess. In Príncipe, the day of the eclipse was cloudy and stormy. Just as totality hit, the clouds thinned a bit, and they frantically snapped a few photos. Months later, at a packed meeting of the Royal Society in London, the results were announced. The measurements were difficult, but they were clear. The starlight had bent. And the amount of bending matched Einstein's prediction, not the old Newtonian one. The next day, headlines exploded. The London Times read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein, the patent clerk from Germany, became a global superstar overnight. Humanity had seen the shape of space. Today, we see this effect, called gravitational lensing everywhere. Massive galaxies bend the light from objects behind them, creating distorted, magnified cosmic mirages. Sometimes we see weird arcs of light, or even multiple images of the same object, like the famous Einstein cross, where a single distant quasar appears as 4 distinct points of light. It's direct, visual proof that space is a pliable medium. And in 2015, we finally heard spacetime itself. The LIGO experiment made the first ever direct detection of gravitational waves ripples in the fabric of spacetime. These waves came from 2 black holes colliding over 1 billion light-years away. As the wave passed through Earth, it stretched and squeezed space by less than the width of a proton, and LIGO's incredibly sensitive detectors picked it up. Spacetime isn't just curved, it can ring like a bell. Part B. Warping time. But Einstein's theory goes even further. If space and time are one fabric, you can't warp one without the other. The theory predicts that the deeper you are in a gravity well, the closer you are to a massive object, the slower time itself will flow. This is gravitational time dilation. Think about the rubber sheet again. A path that follows the curve down into the well is longer than a straight path across the top. In a way, time is like that. It has to work harder to move forward in deep gravity compared to flatter spacetime. For decades, this was just a mind-bending idea. But in the 1970s, it became a very real engineering problem for a technology you use every day: GPS. The Global Positioning System is a network of satellites orbiting about 20,200 kilometers up, each with a super-accurate atomic clock. Your phone figures out where it is by timing signals from several of these satellites. But here's the problem. Those satellites are in a weaker gravitational field than we are. So general relativity says their clocks should tick faster than ours. At the same time, they're zipping around at 14,000 kilometers per hour. So special relativity says their clocks should tick slower. It's a relativistic battle. Which one wins? The math shows that their speed slows their clocks by about 7 microseconds a day, but the weaker gravity speeds them up by 45 microseconds a day. The net result: GPS satellite clocks get ahead of Earth clocks by about 38 microseconds every single day. That sounds tiny, but GPS needs nanosecond accuracy. If engineers didn't correct for that 38 microsecond drift, navigation errors would pile up at a rate of 10 kilometers every single day. Within minutes, your GPS would think your house is a block away. So, built right into the GPS system is a constant correction. The satellite clocks are designed to run a tiny bit slow on purpose, to perfectly cancel out relativity. Every time you use a map on your phone, you are using a system that confirms, moment by moment, that time runs at different speeds in different places. The silent force isn't just warping space, it's warping time. The cosmic consequences and the edge of knowledge. Once you accept that mass curves spacetime, you can follow that idea to its most insane conclusion. What happens if you cram more and more mass into a smaller and smaller space? The curve in spacetime gets deeper and steeper. If you concentrate enough mass, the curve can become so extreme it basically wraps back on itself, tearing a hole in the fabric of reality. That is a black hole. It's not really an asterisk object, it's a asterisk place. A region of spacetime so warped that every possible path, including the path of light, leads to the center. The point of no return is the event horizon. It isn't a physical surface. It's the boundary where the slope of spacetime becomes so steep that you'd need to travel faster than light to get out. Once you cross it, all roads lead down. At the very center of a black hole, our physics just breaks. General relativity predicts a point of infinite density and zero size called a singularity, where the laws of spacetime as we know them stop making sense. This is where the beautiful, smooth world of Einstein's theory slams head first into the weird, probabilistic world of quantum mechanics. And this is the frontier. General relativity describes the very large, planets, stars, and galaxies. Quantum mechanics describes the very small, atoms and particles. Both theories are incredibly successful, but they are fundamentally incompatible. They don't speak the same language. The hunt for a single theory that can unite them, a theory of everything, or quantum gravity, is the biggest challenge in physics today. What really happens inside a black hole? What was the universe like at the very instant of the Big Bang? Is spacetime smooth, as Einstein thought, or is it made of tiny, indivisible pixels of reality? Scientists are exploring some truly wild ideas to find out. String theory suggests everything is made of tiny vibrating strings, and that there might be hidden dimensions of spacetime. Loop quantum gravity imagines that spacetime itself is woven from microscopic, quantized loops. This clash between the cosmic scale of gravity and the tiny scale of the quantum world is where all the action is. If you'd like to do a deep dive into the bizarre search for quantum gravity, let me know in the comments. It's a story that goes to the absolute edge of what we know. But for now, the legacy of Einstein's theory is all around us. From the dance of stars around the supermassive black hole in our own galaxy's center to the expansion of the entire universe, general relativity has proven to be an astonishingly accurate picture of the cosmos. Conclusion. So, we started this journey in a quiet room, just thinking about stillness. We saw how the old Newtonian idea of a gravitational pull, while useful, was just a ghost, an incomplete story. We followed Einstein's happiest thought to a new vision of the cosmos, a four-dimensional landscape of spacetime, bent and shaped by everything within it. We saw the proof in starlight bent by the sun and heard the echo in ripples from colliding black holes. And we found its signature in the phone in our pocket, a device that only works because it knows that time itself is not constant. So the silent force warping your reality right now isn't a force at all. It's the geometry of the universe. It's the curvature of a 4D landscape that you're navigating every second, even when you're perfectly still. The space around you isn't empty. It's an invisible, dynamic substance that determines the fate of galaxies and the ticking of your clock. The next time you feel your feet planted on the ground, remember what's really happening. You're not being held down. You are being actively pushed up, accelerating through a curved reality just to stand still. The ground beneath you isn't just holding you up, it's fighting the very shape of the cosmos to keep you in one place. If this journey bent your mind in the best way possible, consider subscribing for more trips to the edge of reality. And until next time, stay curious. The invisible highways that control the universe. For centuries, our understanding of the universe rested on a simple, intuitive foundation: the feeling of being held to the earth. It's a constant and seemingly straightforward presence in our lives, an invisible cord tethering us to the ground. And yet, modern physics suggests this familiar sensation is not what it seems. It suggests that the most natural state of being is not standing still, but falling, and that this fall is the straightest path any object can take through the cosmos. This idea seems to run contrary to our entire experience of reality. But it appears that everything, from ourselves to the most distant galaxies, is traveling along invisible highways. These paths are not made of any substance, yet they govern the motion of all things. In this exploration, we will trace the evolution of this idea, moving from a universe of mysterious forces to one of pure geometry, and in doing so, come to see that the feeling of weight is merely the sensation of the world preventing us from following our own quiet, effortless course through the fabric of spacetime. From poles to paths, our intimate relationship with gravity begins the moment we are born. We learn its rules with our first steps, with every object we drop and watch fall. It feels like a fundamental pull, a force that draws all things toward the center of the earth. For a long time, this was the pinnacle of scientific thought as well. In the late 17th century, Isaac Newton formalized this intuition. The story of the falling apple prompting him to wonder if the moon, too, was falling, marked a profound leap in understanding. He realized that the same phenomenon that brings an apple to the ground is what holds the moon in its orbit, and what keeps the Earth circling the Sun. The result was his law of universal gravitation, an elegant and powerful equation. F equals g, m1 m2, r squared. This formula was revolutionary. With it, the universe became a kind of grand cosmic clockwork, where the motions of planets could be predicted with astonishing accuracy. It even led to the discovery of Neptune, not through direct observation, but by calculating the gravitational pull of an unseen mass on the orbit of Uranus. Newton's description was a triumph. And yet, a deep question remained, one that troubled Newton himself. How did this force act across the vacuum of space? How could the Sun, millions of miles away, tell the Earth to follow its path? Newton described the what with unparalleled genius, but the how was a mystery. He called it action at a distance, and admitted it was a philosophical absurdity. He had provided a magnificent tool, but the nature of the tool's function remained unknown. This question would wait for over 2 centuries for a new mind, a young patent clerk who would show us that there is no pull at all, only the shape of the universe itself. The happiest thought, the equivalence principle. In 1907, while working at the patent office in Bern, Albert Einstein had what he would later call the happiest thought of my life. The thought was deceptively simple. If a person falls freely, he will not feel his own weight. This single idea, born from a moment of quiet contemplation, would become the foundation of his general theory of relativity. To understand its power, let us consider a thought experiment that Einstein devised, involving an observer in a sealed, windowless room. First, let us place this room on the surface of the Earth. Inside, you feel your normal weight. If you drop a ball, it falls to the floor, accelerating at 9.8 meters per second squared. This is our familiar world. Now, let us transport this same room to the emptiness of deep space, far from any significant gravitational influence. Everything inside is weightless. But then, a rocket attached to the outside of the room begins to fire, pushing it upwards with a constant acceleration of 9.8 meters per second squared. Your feet are now pressed to the floor. If you drop a ball, the floor rushes up to meet it, and from your perspective, it appears to fall with the exact same acceleration it did on Earth. Here is the essential point. From within the windowless room, there is no experiment you could perform that could distinguish between being at rest in a gravitational field and being accelerated through space. This is the core of Einstein's equivalence principle. On a local scale, the effects of gravity are indistinguishable from acceleration. But the thought experiment continues. Imagine the room is back on Earth, but the cable holding it snaps, and it enters a state of freefall. Inside, you would feel completely weightless. An object released from your hand would not fall to the floor but would instead float beside you, as both you and it are falling together. This state of freefall is, in turn, indistinguishable from floating weightlessly in deep space with the rockets turned off. This was the revelation. The force we think of as gravity is not something we feel. The sensation we call weight is not a pull from below. It is the floor, or your chair, or the ground beneath your feet pushing up, constantly arresting your body's natural tendency to fall freely. The ground gets in the way of the path your body wants to follow. Weight is the feeling of this constant, upward acceleration. If an object in freefall feels no force, why then does its path bend toward the Earth? If there is no pull, why do things not simply travel in straight lines? It is because the object is traveling in a straight line, but the definition of a straight line is determined by the curved geometry of the universe itself. Redefining straight, the invisible highways. To understand how a natural path can be curved, we must first reconsider the concept of a straight line. For millennia, a straight line was simply the shortest distance between 2 points on a flat surface. But it appears that the universe itself does not adhere to this simple, flat geometry. To visualize this, we can consider a curved two-dimensional surface we are all familiar with, the Earth. Imagine two travelers beginning a journey at the equator, separated by 1,000 miles. Both decide to walk straight north, using a compass to ensure they never deviate from their bearing. From the perspective of each traveler, their path is perfectly straight. And yet, as they proceed, their paths, which began parallel, will begin to draw closer. Eventually, should they travel far enough, they will meet at a single point, the North Pole. A two-dimensional being living on this surface, unaware of the third dimension, might conclude that some mysterious force was pulling them together. But from our perspective, we can see there is no force. Their paths converged because the very geometry of the surface they were walking on is curved. This straightest possible path on a curved surface is called a geodesic. On a sphere, these geodesics are great circles, the path a commercial airliner follows, for instance, because it is the most direct and efficient route. In 1915, Einstein proposed in his general theory of relativity that this principle applies to the four-dimensional fabric of our universe. He realized that space and time are not separate and static, but are woven together into a single, dynamic entity called spacetime. The central idea, as later summarized by physicist John Archibald Wheeler, is this: mass and energy tell spacetime how to curve, and curved spacetime tells mass and energy how to move. This is the solution to Newton's action at a distance. The sun does not exert a spooky pull on the Earth. Instead, the sun's immense mass creates a deep curvature in the spacetime around it, much like a heavy ball placed on a rubber sheet. The Earth, in its orbit, is simply following a straight path through that curved spacetime. These are the invisible highways of the universe, the geodesics of four-dimensional spacetime. Any object not acted upon by an external force is traveling along one of these paths. A falling apple is not being pulled. It is beginning a journey along its geodesic in the spacetime curved by Earth's mass. There is no force, only geometry. Right now, your body wants to follow its own geodesic, a path of weightless freefall. The ground is simply in the way. The geometry of a fall, geodesics in detail. The notion that we are all following the straightest paths through a curved reality is a profound shift in perspective. But what it means to travel straight through four-dimensional spacetime involves one of our most personal experiences, the passage of time. In relativity, we must distinguish between coordinate time, measured by a distant, stationary observer, and proper time. Proper time is the time that passes on your own wristwatch. It is the time you personally experience as you move along your path. In flat, three-dimensional geometry, a straight line is the path of the shortest distance. One might assume a geodesic in spacetime is the path of shortest time, but here, the theory presents a remarkable consequence. For any object with mass, its geodesic, its natural path of freefall, is the path that maximizes its proper time. Let that idea settle. The trajectory of a falling apple or the orbit of the moon is the path of the longest possible time. An object influenced by gravity alone will move between 2 points in spacetime in such a way that the maximum amount of time passes on its own internal clock. This is why it is often called the path of least action. It is the most effortless route. This helps us understand the twin paradox from a new angle. A twin who travels into space at high speed and returns is younger than the twin who stayed on Earth. This is because the traveling twin had to use rockets to accelerate and decelerate, forcing them off their natural, time-maximizing geodesic. By taking this forced shortcut through space-time, less of their own proper time elapsed. Freefall, it turns out, is the path of maximum aging. Of course, not all things have mass. Light particles, or photons, are massless. They also follow geodesics, but theirs are null geodesics, paths along which zero proper time elapses. From a photon's perspective, no time passes between its emission and absorption. But because light, too, must follow the highways of spacetime, its path can be bent by gravity. In 1919, observations during a solar eclipse by Arthur Eddington confirmed this. Starlight passing near the Sun was seen to bend, its path altered by the Sun's curvature of spacetime, just as Einstein's theory predicted. It was proof that gravity was not a force that pulled on mass, but a feature of the geometry of the universe itself. The cosmic scale, orbits, galaxies, and black holes. With this geometric understanding, the grand structures of the cosmos come into a new, clearer focus. An orbit, for instance, can be understood as a fall that continually misses its target. The International Space Station is not free from gravity. The field at its altitude is nearly 90% as strong as on the surface. The station, and the astronauts within it, are in a constant state of freefall. They are following their spacetime geodesic, but their immense forward velocity means that as they fall down, the Earth curves away beneath them at the same rate. They are perpetually falling around the Earth, which is why they experience weightlessness. The Moon is in a similar state, following the straightest path it can through the spacetime curved by the Earth. The Earth and the other planets are doing the same, each following their own geodesic within the large gravitational valley created by the Sun's mass. The clockwork universe of Newton is replaced by a silent, geometric ballet. Zooming out further, we see galaxies, collections of billions of stars, each star following its geodesic within the collective gravitational well of the whole. Galaxy clusters, the largest gravitationally bound structures we know of, are composed of thousands of individual galaxies, all tracing paths along highways shaped by the combined mass of all the stars, gas, and dark matter in the system. The most extreme expression of this principle is a black hole. Here, an immense amount of mass is concentrated into an incredibly small volume, creating what is called a singularity. This produces such an extreme warping of spacetime that, beyond a boundary known as the event horizon, all possible paths, every single geodesic, point inward. Nothing, not even light, can find a trajectory that leads out. Escape is impossible simply because there are no available paths that lead to escape. A black hole is not an object that sucks things in. It is a region where the geometry of reality itself has become a one-way street. The evidence and the future. This reframing of the universe is a beautiful and compelling idea, but scientific theories require evidence. One of the most tangible confirmations of general relativity is a technology many of us use every day: the Global Positioning System, or GPS. The GPS network relies on satellites with incredibly precise atomic clocks. For the system to work, it must account for the fact that time itself is affected by gravity. Because the satellites are in a weaker gravitational field than we are, their clocks run slightly faster than clocks on the ground. When combined with the effects of their high velocity, the net result is that GPS satellite clocks gain about 38 microseconds every day relative to us. If the engineers who built the system had not programmed in Einstein's equations for curved spacetime, this tiny discrepancy would cause navigational errors to accumulate at a rate of about 10 kilometers each day, rendering the system useless. The fact that your phone can guide you with such precision is a quiet, daily proof of the geometric reality we inhabit. And yet, the story of physics is not complete. General relativity describes the world of the very large with incredible accuracy, but it does not seem to mesh with quantum mechanics, our theory of the very small. The search for a unified theory of quantum gravity is one of the greatest challenges in modern science. Within this search, new ideas are emerging. Some physicists explore the concept of quantum geodesics, wondering if spacetime at the smallest scales is not smooth, but has an inherent wobble or uncertainty. Other avenues of research propose that spacetime itself may not be fundamental, but might be an emergent property of something deeper still. These are the current frontiers, where our understanding of reality is once again being challenged, much as it was by Einstein over a century ago. If this quiet exploration into the fabric of reality has helped unwind your mind, consider liking the video and subscribing to the channel for more journeys into the fundamental questions of our universe. We are always interested to hear your thoughts, so feel free to share in the comments which aspect of this geometric reality you find most fascinating. Conclusion. So, the next time you feel your feet planted firmly on the ground, take a moment to reflect on what is truly happening. You are not being pulled down by a mysterious force. You are an assembly of matter, navigating a dynamic, four-dimensional landscape. The sensation of weight is simply the ground pushing up, preventing you from embarking on your true, natural, and effortless journey along the straightest possible path through the cosmos. A journey along an invisible highway through a curved and magnificent reality. That is the shape of falling. That is the shape of the universe. How Newton's cannonball unlocked perpetual freefall. To stay in orbit forever, you don't need to escape gravity. You just need to fall towards it and miss. It's a simple, mind-bending idea, and it's the secret to how everything from a satellite to the moon itself is in a constant state of perpetual freefall. This idea was born from a 17th-century thought experiment, one involving a massive cannon on an even bigger mountain. And it reveals a beautiful paradox: to fly, you must fall. To circle the globe endlessly, you have to be constantly pulled toward its center. For most of human history, we looked at the heavens and saw perfection, a realm of flawless circles and divine clockwork, completely separate from our messy world down below. Here, things fell. Up there, things just were. They moved in majestic, unchanging paths. How could the same clumsy force that pulls an apple to the ground be responsible for the graceful, eternal dance of the moon? The answer didn't come from a lab, but from inside the mind of one of history's greatest thinkers, Isaac Newton. He didn't need a spaceship or a supercomputer. All he needed was a mountain, a cannon, and a revolutionary spark of imagination. He pictured something so simple it was radical. What if you could fire a cannonball so fast that as it fell, the world curved away beneath it at the exact same rate? What happens then? The cannonball falls, and falls, and falls, but it never hits the ground. It's trapped in a state of perpetual freefall, forever chasing a horizon that's forever running away. It would be in orbit. This single, elegant idea didn't just solve a puzzle. It shattered the barrier between Earth and the heavens. It proved that the laws of physics are universal, that the same force governs both the mundane and the magnificent. So today, Let's climb that imaginary mountain, load that imaginary cannon, and see for ourselves what an orbit truly is. The world before orbit. To really get the genius of Newton's idea, we have to rewind the clock to a time when people had a totally different view of the cosmos. For thousands of years, the universe was split in two: the terrestrial realm, our world, and the celestial realm, the heavens. And these weren't just different places, they played by completely different rules. Here on Earth, the natural state of things was rest. If you threw something, it would eventually slow down and fall. Motion was temporary and always ended with the object coming to a stop. Our world was a place of straight lines and messy, unpredictable arcs. This was the physics of Aristotle, and it dominated Western thought for almost 2,000 years. But if you looked up, you saw a different universe. The heavens were the domain of perfection. The sun, moon, and planets all moved in what everyone believed were perfect circles. Their motion wasn't temporary, it was eternal and unchanging. This wasn't physics, this was divine clockwork. Astronomers like Ptolemy went to incredible lengths to keep this idea alive. When they noticed that planets seemed to slow down, speed up, or even move backward, they didn't question the circle. They just added more circles. They came up with wild, dizzying systems of epicycles, planets moving in small circles that were themselves moving along larger circles, all to make messy reality fit a perfect ideal. In this worldview, the gap between Earth and the sky was fundamental. The laws that made a rock fall to the ground couldn't possibly be the same laws that guided Jupiter across the night. Celestial bodies were made of a fifth element, a perfect substance called ether, totally different from Earth, water, air, and fire. To suggest the moon was just a big rock, subject to the same grubby forces as a stone you'd find in your garden, would have been heresy. The question, how does the moon stay in orbit, wouldn't have even made sense. The moon didn't stay in orbit because of some physical force. It moved in a circle because that was its nature. It was part of a celestial sphere, a giant crystal ball that spun around the Earth, carrying the moon with it. Falling was something that happened on Earth. Things fell towards the center of the universe, which, of course, was the Earth. Since the moon was already in the heavens, it had nowhere to fall to. This was the world that thinkers like Galileo Galilei and Johannes Kepler started to pick apart. Galileo, with his telescope, saw that the moon wasn't a perfect, smooth sphere, but was covered in mountains and craters, just like Earth. He saw moons orbiting Jupiter, proving that not everything revolved around us. Meanwhile, Kepler, using Tycho Brahe's incredibly detailed observations, delivered an even bigger blow. After years of brutal calculations, he figured out that planets don't move in perfect circles at all. They move in ellipses. This was a major crack in the old worldview. The heavens weren't so perfect after all. But even Kepler, who figured out the asterisk what of planetary motion, couldn't explain the asterisk why. What mysterious force from the sun kept the planets on these elliptical paths? The old world was dying, but the new one hadn't been fully born. The stage was set for a revolution, and it would take one more person to connect the dots and see the invisible thread tying the falling apple to the orbiting moon. The universal law. That revolution arrived in the mind of a young man in his early 20s, who had fled Cambridge to his family home to escape the Great Plague of 1665. That man was Isaac Newton. Alone with his thoughts for over a year, in what might be the most productive gap year in human history, Newton laid the groundwork for modern science. He developed his laws of motion, invented calculus, and started thinking about the force that holds the universe together. The famous story, of course, involves an apple. As Newton himself later told it, he was in a garden when he saw an apple fall from a tree. And while the part about it bonking him on the head is probably just a good story, the core idea is true. He wondered. This force that pulled the apple to the ground, gravity, how far does it go? Does it stop at the treetops? Or the mountaintops? Or could it, maybe, reach all the way to the moon? And that was the big question. It sounds simple to us now, but at the time it was a wild leap of imagination. He was saying that the force acting on the apple was the exact same force acting on the moon. He was proposing that gravity wasn't just an earthly thing, but a universal one. To test this idea, Newton first needed to understand motion. Building on Galileo's work, he came up with his first law of motion. An object in motion will stay in motion, in a straight line, unless a force acts on it. That's inertia. You feel it all the time. When a car is moving at a steady speed, you feel at rest. It's only when the driver hits the gas, the brakes, or turns the wheel that you feel a force pushing or pulling you. Newton realized this had to apply to the heavens, too. The moon wasn't moving in a straight line, it was moving in a near circle around the Earth. So, some force had to be constantly pulling on it, yanking it away from the straight path it wanted to follow. His guess for that force? Earth's gravity. The moon, in essence, was constantly falling toward the Earth. But that leads to a paradox. If the moon is always falling toward us, why doesn't it crash? And that's where the apple comes back in. The apple falls straight down because it has no sideways motion to speak of. But the moon does have sideways motion. A lot of it. Newton realized the moon is falling. Every single moment, it's falling towards the Earth, just like the apple. But because of its incredible sideways speed, as it falls, the round surface of the Earth curves away from it. Gravity pulls the moon down, but the moon's inertia carries it forward. The two effects are so perfectly balanced that the moon stays at roughly the same altitude, forever falling toward a ground it can never hit. To prove it, Newton had to figure out how gravity changes with distance. He deduced it must follow an inverse square law. This just means that if you double your distance from something, its gravitational pull gets 4 times weaker, 2 squared. Triple the distance, and it's 9 times weaker, 3 squared. Now, he could finally do the math. He knew the approximate distance to the moon, about 60 times Earth's radius. He knew how long the moon took to make one orbit, about 27.3 days. And he knew the force of gravity on Earth's surface, how fast the apple falls. Using his inverse square law, he could calculate how strong Earth's gravity should be at the moon's distance. Then, using the moon's speed and orbital path, he could calculate how much the moon was actually falling, how far it curved away from a straight line path every second. The two numbers matched. As he famously understated, they answer pretty nearly. The small difference was due to the slightly off measurements for the Earth's radius he had at the time. When he recalculated years later with better data, the numbers clicked into place almost perfectly. It was a stunning confirmation. The force that pulls an apple to the ground is the same force that holds the moon in its orbit. The heavens and the Earth were united under one law. Gravity was universal, but explaining it with math is one thing. To make people feel it, he needed something more visual, a thought experiment so powerful it could rewire our entire understanding of falling and flying. He needed a cannon on top of a mountain. The cannon on the mountain. This is where Newton's genius for making the complex feel simple really shines. To explain his idea that the moon is just a falling object, he came up with a thought experiment that starts by climbing to the top of the tallest mountain imaginable. Imagine we're standing there with him. The mountain is so tall its peak is above Earth's atmosphere, so we can ignore air resistance. In front of us is a huge cannon, aimed perfectly level with the ground. Shot number 1. The basics. With a normal amount of gunpowder, we fire the cannon. The cannonball shoots out, but gravity immediately grabs it. It follows a familiar curve, a parabola, and after a few miles, it slams into the ground. No surprises here. It's what things do. This first shot is our baseline. An object with forward speed falls in a curve and hits the ground. Simple. Shot number 2. Faster and farther. But what if, Newton might ask, we use more gunpowder? We reload, packing a much bigger charge. Boom! The cannonball bursts out at a much higher speed. It flies much, much farther, hundreds of miles. But the whole time, gravity is still pulling. Its path is still a curve, just a much longer, stretched out one. Eventually, it hits the Earth. But something interesting happened on that shot. The cannonball went so far that the curvature of the Earth started to matter. As it flew, the ground beneath it was literally dropping away. It had to fall a little bit extra just to catch up with the curving surface. Its journey was longer because the planet itself is round. This is the key. So, we do it again. More gunpowder. More speed. Each shot sends the cannonball screaming farther around the planet. One makes it a quarter of the way around the globe before landing. The next makes it halfway around the world. With each shot, the arc of the fall gets longer and shallower, more closely matching the gentle curve of the Earth itself. Shot number 3. The aha moment. Now, for the final shot. We load the cannon with a very specific, critical amount of powder. We're aiming for a precise speed. For a low Earth orbit, that's about 7.8 kilometers per second, or roughly 17,500 miles per hour. We fire the cannon. The cannonball launches horizontally. In the first second, gravity pulls it down about 5 meters. But in that same second, the cannonball has traveled nearly 8 kilometers sideways. And over that distance, the Earth's surface has curved downwards by, you guessed it, about 5 meters. The cannonball falls, but the ground falls away beneath it at the exact same rate. It continues. In the next second, it falls another 5 meters away from the straight-line path it wants to take, but again, its massive forward speed has carried it over the horizon, and the Earth has once again curved away perfectly to match its fall. The cannonball is now in a state of perpetual freefall. It is continuously falling towards the Earth, but its horizontal motion is so fast that it constantly misses the ground. It will trace a complete circle around the planet and, if our mountain is tall enough, return right back to where it started, ready to do it all over again. That is an orbit. It's not about escaping gravity. It's the art of falling, perfectly balanced between the inward pull of gravity and the forward momentum of inertia. The cannonball isn't being held up by anything. It's just in a continuous descent around a sphere. And beyond. Ellipses and escape. But what if, Newton might say, with a glint in his eye, we add even more gunpowder? What happens if we fire the cannonball faster than that 7.8 kilometers per second? Its forward momentum is now a bit too strong for gravity to bend into a perfect circle. The path becomes a stretched-out oval, an ellipse. The cannonball travels out to a high point, slowing down, then falls back toward Earth, speeding up as it swings past the low point, just like Kepler observed the planets doing. And if we keep adding speed, at about 11.2 kilometers per second near the surface, we hit another critical threshold, escape velocity. At this speed, gravity is still pulling on it, but its initial energy is so great that gravity will never be strong enough to bring it back. It will escape Earth's gravity and drift off into space forever. So, from this one simple thought experiment, Newton explained it all. Too slow, you crash. Just right, you get a circular orbit. A bit faster, an elliptical orbit. Much faster, and you escape. The entire rulebook for celestial motion was written by a cannon on a mountain. The proof in the sky. Newton's cannon was a masterpiece of imagination. But the ultimate test of any scientific idea is reality. Newton didn't have to look far for his proof. He just had to look up. The falling moon. The moon was Newton's original inspiration, and it became his ultimate proof. He applied the exact logic of his cannonball to it. The moon, he said, is in a constant state of freefall. It has tremendous sideways velocity that keeps it from crashing, but it is falling. He did a brilliant calculation to prove it. First, he calculated how far an apple falls in 1 second on Earth. Roughly 4.9 meters. Next, using his inverse square law, he calculated how much the moon should fall in 1 second. The moon is about 60 times farther from Earth's center than the apple. So, gravity there should be 3,600 times weaker. This means the moon should fall about 1.36 millimeters in 1 second, about the thickness of a dime. Finally, he calculated how much the moon actually falls. Using its orbital period of 27.3 days, he figured out how much its path deviates from a straight line every second. The answer? About 1.36 millimeters. The numbers matched. The moon falls towards the Earth by the exact amount his law of gravity predicted. The cannonball wasn't a fantasy. Its perfect twin had been circling our planet for billions of years. The International Space Station, the modern cannonball. Fast forward 300 years. Humanity has built its own cannonballs. The most spectacular example is the International Space Station, ISS. This football field-sized laboratory is the ultimate proof of Newton's idea. The ISS orbits at an altitude of about 400 kilometers, 250 miles. Many people think there's no gravity up there, but that's one of the biggest misconceptions in science. In reality, the gravity at the ISS's altitude is about 90% as strong as it is on the surface. If you could build a 400-kilometer tall ladder and stand on it, you'd feel almost your normal weight. So why do astronauts float? They are floating for the exact same reason Newton's cannonball stays in orbit. They are in a constant state of freefall. To stay in orbit, the ISS has to travel at a blistering 7.66 kilometers per second, or over 17,100 miles per hour. At that speed, it circles the entire planet every 93 minutes, giving the crew about 15 sunrises and sunsets every day. Just like the cannonball, the ISS and everything inside it are perpetually falling towards Earth. But their incredible forward speed means the curve of their fall perfectly matches the curve of the planet. The astronauts float not because there's no gravity, but because there's no ground to stop their fall. Think of it like being in an elevator when the cable snaps. For those few terrifying seconds, you'd be in freefall. If you let go of a ball, it wouldn't drop to the floor. It would just float in front of you, because you, the ball, and the elevator are all falling together. The ISS is that elevator, but it's moving sideways so fast that it never hits the ground. Every time you see an astronaut tumbling through the space station, you are watching Newton's cannonball in action, a state of controlled, perpetual, beautiful freefall. This is the principle behind our entire space-faring civilization. Every satellite for GPS, weather, and communications is just another cannonball, placed in a precise orbit, simply falling and missing. The cosmic implications. The power of Newton's idea is that it doesn't stop with a cannonball or the moon. Its implications are literally cosmic. He hadn't just explained satellites, he'd found the organizing principle of the entire universe. The logical next step was to look outward. The Sun, being so much more massive than the planets, had to be the gravitational anchor of the solar system. Earth, Mars, Jupiter, they were all just cannonballs in orbit around the Sun. Our own planet is falling. Right now, you are hurtling through space at about 30 kilometers per second, or 67,000 miles per hour. We are all passengers on a giant, spherical cannonball in a constant state of freefall around the Sun. We don't fly off into space because the Sun's gravity is always pulling us in, bending our path into a year-long ellipse. And we don't spiral into the Sun because our planet's sideways momentum keeps us perpetually missing it. Every planet is in this same cosmic dance. Distant Neptune plods along slowly, where the Sun's pull is weak. Mercury whips around in just 88 days. Its high speed just enough to balance the Sun's ferocious gravity so close in. Kepler's laws, which were just observations about how planets moved, were finally explained by why. But the scale keeps going up. Our Sun is a cannonball, too. Along with hundreds of billions of other stars, it's in a state of perpetual freefall around the supermassive black hole at the center of our Milky Way galaxy. It takes our Sun about 225 to 250 million years to complete one grand orbit, dragging all of us along for the ride. Even galaxies are falling. Our Milky Way and the nearby Andromeda galaxy are pulling on each other, falling towards each other at over 100 kilometers per second, destined to merge in a few billion years. And on the grandest scale, clusters of galaxies are falling toward even larger superclusters, all orchestrated by the simple rule Newton first imagined with his cannon. From the tiniest moon to the largest structures in the cosmos, everything is falling. The universe isn't a static clockwork machine. It's a dynamic, evolving, and far more exciting place, a cosmic dance of falling and missing. And it all started with a simple question. What if you could throw something so fast that it just kept missing the ground? The answer turned out to be the secret of everything. Thinking about these cosmic scales is wild. The idea that our entire planet is in freefall, just like an astronaut, really changes how you see our place in the universe. We've talked about the Earth falling around the Sun and the Sun falling around the galaxy. But what orbit truly blows your mind? Is it the strange dance of Pluto's moons, or stars whipping around the edge of a black hole? Let me know in the comments below. And if you're enjoying this journey into how the cosmos works, consider subscribing so you don't miss our next adventure. Conclusion. So, we're back from the peak of Newton's imaginary mountain, the sound of that final cannon shot still ringing in our ears. We started with a paradox. To stay in the sky, you must fall. And through a 17th century thought experiment, we've unraveled its truth. An orbit isn't about floating, and it's not a fight against gravity. It's a surrender to it. It's what happens when an object's forward speed is so perfectly balanced against gravity's inward pull that its path of descent exactly matches the curve of the planet it's falling around. It is controlled, perpetual freefall. This one idea, born from a simple image, dissolved the ancient barrier between a flawed Earth and a perfect heaven. It showed us that the same law that governs a falling apple governs the arc of the moon, that our world is a celestial body, and that we are all astronauts on a planetary spaceship. Today, the sky is filled with the children of Newton's cannonball. Thousands of satellites trace their paths based on these same rules. The women and men on the International Space Station live in a state of constant freefall, a living testament to this idea. And beyond them, the planets, stars, and galaxies all perform the same cosmic ballet, falling and missing, in a dance that has gone on for billions of years. The next time you look up at the night sky and see the moon, or catch the fleeting streak of a satellite, remember what you're really seeing. You're not watching something held up by a mysterious force. You are watching something fall. And in its endless descent, you are seeing the beautiful, mind-bending reality of perpetual freefall. How fast must you jump to never land again? Every time you jump, you're declaring a tiny, one-person war on the entire planet. A war you are always destined to lose. The Earth, with its 6 trillion kilograms of mass, pulls you back down every single time, without fail. It is the most predictable defeat in the universe. But what if you could win? What if you could bend your knees, spring up, and make one single jump that never ends? This is the story of how fast you'd have to leap to break free from Earth forever, and the almost unimaginable power it would take to turn that leap into an endless journey to the stars. The invisible war. Think about that feeling. That brief moment of weightlessness at the very top of a jump. For a fraction of a second, you just hang there, caught between the sky and the ground. In that instant, your upward speed is exactly zero, and the only thing acting on you is the relentless, invisible force of gravity. It's such a constant presence in our lives, we barely even notice it. We just call it weight. It's the reason we don't float off into space, the reason apples fall from trees, and the reason that every jump, no matter how high, has to end with a return trip. This force, gravity, is basically the planet's way of saying, you belong to me. Every particle of your body is being pulled toward every particle of the Earth. The sum of all those tiny pulls is a constant, downward acceleration of 9.8 meters per second, every second. When you jump, you're momentarily overpowering that pull. You're pushing against the entire mass of the planet with just the muscles in your legs. For one glorious moment, your force is greater. You accelerate up and away. But gravity is patient. It never gets tired. The exact moment your feet leave the ground, it starts chipping away at your speed. 9.8 meters per second, subtracted from your velocity, every single second. You rise, you slow, you stop, and then you fall. The war is over in an instant, and the Earth always wins. We just accept this. Up is hard, down is easy. You could say we live our lives at the bottom of a deep, invisible well. Imagine a valley so vast its slopes are too gentle to even see. Everything you throw up, a ball, a rock, yourself, eventually rolls back down to you. Throw it harder, and it'll go higher, but it always comes back. This is our reality. We are inhabitants of a gravity well. But the question that drives our story is a rebellious one. It asks, is this well infinitely deep? Or is there a speed, a single burst of energy, so great that you could leap from the bottom and not just reach the other side, but fly out of the valley entirely, never to return? Could you, with a single push, win the war against gravity, once and for all? The answer is yes. But to figure out how, we have to stop thinking about a jump and start thinking about an escape. The dream of a bigger leap. Let's start our journey out of this gravity well not with a jump, but with a simple throw. You're in a field, you toss a ball straight up. It goes up, slows down, comes back. Simple. You throw it harder. It goes higher, but it still comes back. But what if you throw it not just up, but forward? It travels in an arc, a graceful curve called a parabola. The faster you throw it horizontally, the farther it goes. Throw it at the speed of a pro baseball pitcher, and it lands hundreds of feet away. Throw it with the speed of a bullet, and it lands miles away. Now, let's take a little leap of imagination. Picture yourself on a mountain so tall its peak pokes out above the atmosphere, so we can ignore air resistance. And you're not throwing a ball anymore, you're firing a cannon. You fire the first shot. It flies for miles before arcing back down to Earth. You add more gunpowder. The next one goes faster and travels even farther around the planet before it lands. You keep upping the speed. The cannonball makes it a quarter of the way around the world. Then halfway, something weird is happening. As the cannonball flies, the Earth's surface is curving away underneath it. The cannonball is falling, sure, but the ground is also falling away. If you could just get the speed exactly right, you could fire it so fast that the rate it falls toward Earth perfectly matches the rate Earth's surface curves away from it. And if you did that, the cannonball would just keep falling. Forever. It would never get any closer to the ground. It would fall all the way around the planet and, if you're not careful, smack you in the back of the head. You've just made a satellite. You've achieved orbit. This specific speed, near the Earth's surface, is about 7.8 kilometers per second, or roughly 17,500 miles per hour. At this speed, you haven't escaped gravity. You're in a perfect, perpetual stalemate with it. Gravity is still pulling, but your sideways motion is so fast that you just keep missing the ground. This amazing thought experiment wasn't invented for a sci-fi story. It was dreamed up over 300 years ago by the guy who first gave us the math to understand gravity, Isaac Newton. And it holds the key to our whole question. If a certain speed puts you in a stalemate with gravity, what happens if you go faster? The ghost in the machine. Newton's universe. To really get what it means to escape, we have to go back to the 17th century. Back then, the world was a place of deep mysteries. People knew things fell down, and they knew the planets moved across the sky, but they saw these as two totally separate things. One was for here on Earth, the other was for the heavens. It was Isaac Newton who had a moment of pure genius and realized they were one and the same. The story of the apple falling on his head is probably a bit of an exaggeration, but it gets the core of his idea right. Newton saw an apple fall, and then he looked up and saw the moon. And he asked a question that would change everything. If gravity pulls the apple, does it also pull the moon? He figured that the moon, in a way, is falling. Just like his cannonball, the moon is constantly falling toward the Earth. But its incredible sideways speed, a leftover from its formation billions of years ago, means it's always missing. This was a revolution. The same force that drops an apple from a tree also choreographs the dance of the planets. It was universal. Newton didn't just stop there, either. He gave this force a mathematical formula, an equation that became a cornerstone of physics, the law of universal gravitation. The law says that the gravitational force between two objects depends on two things: how massive they are, and how far apart they are. More mass means a stronger pull. Farther apart means a weaker pull. Specifically, the force drops off with the square of the distance. If you get twice as far away, the force is 4 times weaker. 10 times farther, it's 100 times weaker. And that is the key. Gravity's reach is infinite, but it gets weaker and weaker the farther you go. This means the gravity well we're in isn't a straight-walled pit. Its slopes get gentler the higher you climb. And that implies that if you could throw something hard enough, it could gain altitude so fast that gravity's pull weakens faster than it can slow the object down. It would keep slowing, sure, but never quite enough to stop and fall back. It would just coast away forever, its speed getting closer and closer to zero, but never reaching it. Newton had just described the concept of escape velocity. He laid out the theory for leaving a planet. He realized that if his cannonball was fired faster than orbital speed, its path would stretch into an oval, an ellipse. Faster still, and the ellipse stretches out farther and farther. And at one specific, magic speed, the ellipse breaks open. It becomes a new shape, a parabola. An open-ended path that never comes back. That speed is what we call escape velocity. It's not about overpowering gravity with a continuous push, like a rocket. It's about having enough juice in that initial kick to coast away forever, with no more help. Newton gave us the why. He set the rules of the game. Now, we can use his law to figure out the how. How fast, exactly, do you have to be going to win the war? The magic number. Alright, we've worked through the concepts, from simple jumps to orbiting cannonballs. Now it's time to get the number. The one speed that separates a finite leap from an infinite journey. This is where we go from philosophy to physics. The idea behind calculating escape velocity is a beautiful duel between two kinds of energy. First, you have kinetic energy, the energy of motion. The faster you go, the more you have. Second, there's gravitational potential energy. Think of this as negative energy. It's the measure of how bound you are inside the gravity well. To escape, your kinetic energy has to be just enough to cancel out your gravitational potential energy. You need enough energy to perfectly balance out your stay energy. When you set those two energies to equal each other and solve for the velocity, you get this beautiful little equation. V_e equals square root 2gm r. Let's quickly break that down. V_e is escape velocity, our magic number. G* is the universal gravitational constant, a tiny number that sets the strength of gravity in our universe. M* is the mass of the planet you're trying to escape. In our case, the colossal mass of Earth. R* is the radius of that planet, basically your distance from its center. See what's missing? The mass of the thing that's escaping. A feather, an elephant, or you. You all have to hit the exact same speed to break free from Earth. The difference, as we're about to see, is the mind-blowing amount of energy it takes to get each of you up to that speed. So, let's plug in the numbers for Earth. We take the gravitational constant, the mass of the Earth, 5.9722 times 10 to the power of 24 kilograms, and the radius of the Earth, about 6,371 kilometers. We run the math, and we get our number. 11.2 kilometers per second. That's 11,200 meters every single second. It's about 40,320 kilometers an hour, or just over 25,000 miles per hour. This is not the speed of a car. It's not the speed of a jet. It's a speed that's hard to even wrap your head around. It's 33 times the speed of sound. If you could move that fast across the ground, you could circle the entire planet in under an hour. And remember, this isn't a speed you build up to. Escape velocity is the initial speed you need from a single burst. It's the speed your body would have to be moving the very instant your feet left the ground. So, the answer to our first question, how fast must you jump, is 11.2 kilometers per second. But that answer immediately opens up a much more terrifying question. What would it actually take to do that? What is the real cost of a single, perfect jump to freedom? The energy of a god. We have the speed, 11.2 kilometers per second. Now we have to face the consequences. Basic physics tells us that to get a mass moving at a certain speed, you need kinetic energy. The formula is E_k equals 1/2 mv squared. Energy equals 1/2 the mass times the velocity squared. Let's say an average person weighs about 80 kilograms. Now, let's plug our numbers into that equation. We take our 80 kilograms person and get them to 11,200 meters per second, instantly. The result is just ridiculous. The energy required for that one jump is about 5 billion joules. 5 gigajoules. A number that big is pretty meaningless without something to compare it to. So let's try. 5 billion joules is the energy equivalent of about 1.2 tons of TNT. This isn't a jump. This is a massive bomb going off. The energy release would be on par with some of the largest conventional weapons ever made. It's the same energy you'd get from burning over 100 gallons of gasoline, all in a single, instantaneous flash. It's the energy of a powerful, positive charge lightning bolt. The kind that strikes from the top of a thundercloud, and you would be standing at the center of it. If we look at it from a power perspective, power being energy released over time, the numbers get even more absurd. Let's say the jump itself takes half a second. To unleash 5 billion joules in that time would demand a power output of 10 billion watts. 10 gigawatts. A large nuclear power plant produces about 1 gigawatt of power. So for that split second, your legs would need to generate the power of 10 nuclear power stations combined. So what would this jump actually look like? It wouldn't look like a jump. It would be an apocalypse. The moment 5 billion joules of energy were released at your feet, the ground would vaporize, creating a massive crater. The air around you would be superheated into plasma, creating a blinding flash and a deafening shockwave that would flatten everything for miles. And you? The human body isn't built to handle these forces. The acceleration needed to go from 0 to 11.2 kilometers per second in an instant is millions of times the force of gravity. You wouldn't be a person anymore. You'd be a cloud of atoms, a puff of smoke at the heart of a cataclysm. So, the physical act of a human jumping to escape velocity isn't just impossible, it's self-annihilating. The very energy that would free you from Earth's gravity is the same energy that would obliterate you and a good chunk of the surrounding landscape. You'd win the war, but you wouldn't be around to celebrate. An interplanetary pogo stick. This rule is universal. Anything with mass has a gravity well, and so it has an escape velocity. The only thing that changes is the number, depending on the mass and size of the world you're on. So let's take our impossible super jump on a tour of the solar system. First stop, Earth's moon. The Moon is way smaller and less massive than Earth, with only about 1/6 the gravity. Its grip on you is much weaker. Plugging the Moon's numbers into our equation gives an escape velocity of just 2.4 kilometers per second. That's still incredibly fast, about Mach 7, but it's a huge drop from Earth's 11.2 kilometers per second. The energy needed is about 20 times less. Still a catastrophic event for our jumper, but it shows how much easier it is to leave a smaller world. Next, let's head to Mars. The red planet is a good middle ground. It's more massive than the Moon but only about half the size of Earth. Its escape velocity is 5.0 kilometers per second. Again, much less than Earth's, which is a big reason why Mars is seen as a key stepping stone for humanity's future in space. Launching from Mars would take way less fuel and energy than launching from home. Now for the big leagues. Let's travel to the king of our solar system, Jupiter. Jupiter is a monster, more than 300 times as massive as Earth. Its gravity well is more like a chasm. Standing at the top of its cloud layers, the escape velocity is a mind-boggling 59.5 kilometers per second. That's over 5 times Earth's escape velocity. And since energy scales with the square of the velocity, the energy needed to escape Jupiter is more than 25 times greater than escaping Earth. Jupiter is a gravitational prison. And what about the center of it all? The Sun. If you could somehow stand on the Sun's photosphere and jump, you would need to hit a speed of 617.6 kilometers per second to escape its colossal gravity. That's almost 1.4 million miles per hour. This cosmic tour reveals a fundamental truth: gravity sculpts the universe. It dictates which worlds have atmospheres and which are barren rocks. The gas giants are giant precisely because their immense gravity could hold onto light gases like hydrogen and helium, while smaller worlds like Earth and Mars couldn't. And we can take this to its logical conclusion. What happens when something is so massive and so dense that its escape velocity becomes equal to the fastest speed in the universe, the speed of light? Now you're talking about a black hole. Theorized using these very same Newtonian principles way back in the 18th century, a black hole is the ultimate gravity well. If an object is massive and dense enough, you get to a point, the event horizon, where the escape velocity is faster than light. And since nothing can travel faster than light, nothing can escape. Not a rock, not a rocket, not even light itself. The war with gravity is lost before it even starts. The well becomes a bottomless pit. Our simple question about a jump has led us to the most extreme objects in the cosmos. It all follows the same fundamental rule that governs the leap of a child, the orbit of the Moon, and the terrifying silence of a black hole. The real escape artists. Okay, so jumping is clearly not the answer. The instantaneous energy release is just too violent. But the problem doesn't go away. If you want to get to space, you have to pay that energy toll. You have to somehow gain the energy equivalent of an 11.2 kilometers per second velocity. So how do we actually do it? The answer is, we cheat. We do it slowly. And that is the entire principle behind a rocket. A rocket doesn't even try to hit escape velocity in one go. It uses continuous thrust. It's like climbing a very, very tall ladder instead of trying to jump to the roof. A rocket engine is basically a controlled, continuous explosion, blasting hot gas down to push the rocket up. It fights gravity every single meter of the way in a sustained, grueling battle. But here's the trick. By the time a rocket has burned through its fuel and reached a high altitude, it has done the necessary work to overcome the gravity well. The total energy it has spent is the same as in our impossible jump, plus a whole lot more to fight air resistance and carry all that heavy fuel. Engineers have even found cleverer ways to cheat. We launch rockets eastward from near the equator to get a free speed boost from the Earth's own rotation. We often first enter a stable low Earth orbit, like a parking spot in space. From there, it takes way less energy to fire the engines again and go from orbital velocity, 7.8 km per second, to escape velocity, 11.2 km per second. This is what makes missions to the Moon and other planets possible. And the cheating gets even more elegant. Probes like the legendary Voyager 1 and 2, now in interstellar space, used gravity itself to escape. They performed gravitational slingshots, flying close to huge planets like Jupiter and Saturn. By timing their approach just right, they essentially stole a tiny bit of the planet's massive orbital energy, flinging themselves to higher and higher speeds. They turned the enemy's own strength against it. Conclusion: so we come back to where we started. That simple, hopeful leap into the air. We know now that the line between falling back and flying away forever is a hard, bright line drawn by physics. It's a speed, 11.2 km per second, and an amount of energy so vast it would tear us to pieces. The dream of winning the war on gravity with a single jump is a beautiful impossibility. But the story doesn't end there. It ends with human ingenuity. It ends with us, a species that for millions of years was stuck on this planet, staring up at the sky and figuring out the rules of the game. We can't jump to the stars, but we have learned how to climb there. We found ways to pay the energy price, not with the brute force of a single leap, but with the sustained fire of a rocket and the subtle grace of a gravitational dance. Every time you feel that familiar tug, remember the magic number. Remember the invisible well you live in. And remember that while we might always lose the tiny war of a simple jump, through understanding the universe, we have found a way to win the larger one, and begin our own endless journey among the stars. The principles of escape velocity don't just apply to planets. They govern everything with gravity. To see what it would take to escape the pull of the most extreme objects in the universe, the cosmic prisons known as black holes, click on the video here. What falling forever does to the human body. What if you started falling, and just never stopped? Not in a terrifying, wind-screaming plunge, but a slow, gentle drift. For years. Imagine you're suspended in an endless void, in a state of perpetual freefall that is, for all intents and purposes, true zero gravity. Long before humans existed, life was already experimenting. Bodies grew where no bodies had grown before, shaped by chance, survival, and the fundamental forces of their environment. The human body is no different. It's an intricate machine forged over millions of years by the constant, unwavering force of Earth's gravity. Our very architecture, from the density of our bones to the powerful pump of our heart, is a direct response to this relentless pull. So what happens when you take that cornerstone away? This is a journey through that question. We'll follow the biological story of a person trapped in this exact scenario, to see what happens when the most fundamental force of our existence is stripped away. It reveals a fascinating truth. Our bodies are built for a fight, and without that fight, they become something else entirely. Something quietly strange. The first 72 hours, the shock of weightlessness. The fall begins, not with a jolt, but with a gentle drift into nothingness. The first sensation isn't terror, but a profound confusion. Your body, an instrument finely tuned to gravity, is suddenly playing a song it doesn't recognize. The first system to notice something is wrong is the vestibular system, deep within your inner ear. What's so intriguing about this system is how it works. On Earth, tiny calcium crystals called otoliths rest on sensory hairs, constantly telling your brain which way is down. They're your biological gyroscope. But now, they're floating aimlessly. The signal for down is just gone. Your brain, deprived of this crucial input, receives a storm of contradictory information. Your eyes see a static, featureless void, but your inner ear is screaming that you're tumbling in all directions at once. This sensory conflict triggers a bizarre response known as space adaptation syndrome. For up to 70% of astronauts, this period is marked by vertigo and nausea as the brain tries to make sense of the new rules. While your mind is reeling, another, more subtle transformation is already underway. It begins with your blood. On Earth, gravity pulls fluids down, and your cardiovascular system is built to fight this, powerfully pumping blood up to your brain. In this endless fall, that powerful system keeps working, but now it's unopposed. The result is a dramatic fluid shift. About 2 liters of blood and other fluids surge upward into your torso and head. The feeling is deeply strange. Your legs begin to feel thin, a phenomenon astronauts call bird legs. At the same time, your head becomes congested, and your face puffy and swollen in a condition nicknamed moon face. What's fascinating is how the body interprets this. It doesn't see it as a shift. It thinks there's a massive, sudden increase in the total amount of water in your body. It panics and sends an emergency signal. We're overloaded. The brain responds based on its earth-bound programming, triggering a diuretic effect. Your kidneys start working overtime to expel this phantom excess of water, and your thirst mechanism is suppressed. Within these first 72 hours, you become a biological paradox. Your head feels swollen while your body is dehydrating, and every signal from your inner ear is a lie. This is the initial shockwave. But it's just the prelude. Your body has only just realized its lifelong battle is over. And now, system by system, it will begin to adapt in ways that are quietly strange. The first month, the great unburdening. As the first week bleeds into the second, the initial sickness begins to fade. Your brain, in a remarkable feat of neuroplasticity, starts to ignore the chaotic signals from your inner ear and relies almost entirely on your eyes. The vertigo is replaced by a strange new normal. The feeling might even be one of liberation. But this feeling is a deception. It's the calm before a quiet, systematic unraveling, a process that begins with your muscles. The human body is ruthlessly efficient. It operates on a strict, use it or lose it policy. On Earth, even sitting still is an act of resistance against gravity. The large, powerful, anti-gravity muscles of your legs and back are the primary soldiers in this fight. In your endless fall, that fight is over. Your body, recognizing this state of profound ease, deems its muscular architecture an unnecessary, metabolically expensive luxury. The command to dismantle begins. This process is called muscle atrophy, and it happens with surprising speed. Within just the first 5 to 11 days, you can lose up to 20% of the mass in certain muscles. The process starts with the most important ones, like your calf muscles and the powerful extensors of your back. They were built to keep you standing tall. Now, they have no purpose. At a cellular level, the change is drastic. The body simply stops sending resources to repair and maintain these now redundant tissues. The muscle fibers themselves shrink. They don't just get smaller, they fundamentally change, becoming weaker. As your muscles retreat, your cardiovascular system starts its own journey of adaptation. The heart, after all, is a muscle, and its job has just become significantly easier. The left ventricle, the chamber that pumps oxygenated blood to the whole body, begins to remodel itself. Studies on astronauts show that the heart can become slightly smaller and more spherical as it settles into a more leisurely pace. This is cardiovascular deconditioning. This is compounded by another change. The body has now adjusted to a lower fluid volume, and part of this adjustment involves making fewer red blood cells. With less demand for oxygen from shrinking muscles, the body dials back production. This leads to a condition known as space anemia. You are becoming physically weaker, and the very system for delivering fuel is weakening right alongside you. By the end of the first month, a silent, systemic unraveling has taken place. You are floating in a state of perfect, effortless calm, while your body has begun to diligently and efficiently take itself apart. The first year, the skeleton begins to dissolve. As the months drift by, the process of decay accelerates, moving from your muscles to the very framework of your existence. your skeleton. What happens inside your bones is slow, invisible, and a fascinating example of the body's strange logic. What's so interesting about bone is that it's not a static, rock-like substance. It's a living tissue in a constant state of renewal called remodeling. Your skeleton is in a balanced conflict between two types of cells: osteoclasts, the demolition crew that dissolves old bone, and osteoblasts, the construction crew that lays down new bone. The crucial factor that maintains this balance is mechanical stress. Every step you take sends a signal to the osteoblasts to keep building. In your endless fall, there is no mechanical stress. The signal to build has vanished. But the demolition crew, the osteoclasts, don't stop. The result is a profound imbalance. Bone is being broken down, but it is not being replaced. The statistics from NASA are intriguing. In microgravity, astronauts lose bone mineral density at a rate of 1% to 1.5% per month *, primarily in weight-bearing bones like the lower vertebrae, hip, and femur. This rate of decay is staggering, roughly 10 times faster than the bone loss seen in an elderly person with advanced osteoporosis. After one full year, the consequences are severe. You would have lost between 12% and 18% of the bone mass in your hips and spine. Your skeleton, once a resilient frame, is becoming porous and brittle. And this internal dissolution has a bizarre side effect. As your osteoclasts break down bone, they release calcium into your bloodstream, a condition called hypercalcemia. Your body scrambles to deal with this mineral surplus, commanding the kidneys to filter it out. This state, hypercalciuria, turns your urinary tract into a high-risk zone. The high concentration of calcium salts makes it incredibly likely that painful kidney stones will form. There is a strange irony here. You are trapped in an environment of absolute stillness, yet your own body could suddenly subject you to intense pain. Your skeleton is dissolving to support a body that needs no support, and in the process, it's creating new problems from the inside out. After 1 year, your structural integrity is vanishing. You are becoming a fragile ghost, haunted by the memory of a force your body can no longer find. The breakdown is happening from the inside out, a strange adaptation to a world without weight. If you're fascinated by the incredible and sometimes bizarre limits of the human body, make sure to subscribe and hit the bell so you don't miss our next journey into the unknown. The multi-year descent, systemic failure. The first year was a period of rapid adaptation. The years that follow are a slow, grinding journey into systemic change. The initial shifts have now become chronic conditions, cascading through your body. One of the most intriguing transformations happens in your eyes. That constant, upward pressure from the fluid shift never truly goes away. This permanently elevated intracranial pressure begins to exert a force on the softest structures it can find, the back of your eyeballs and the optic nerves. This leads to a condition NASA has identified as a serious long-term risk: spaceflight-associated neuroocular syndrome, or SANS. The pressure physically deforms your eyes. The back of the eyeball flattens. The head of the optic nerve begins to swell, a condition called optic disc edema. The visual consequences are deeply unsettling. You would become progressively farsighted, your vision growing blurry. While this is often reversible on Earth, for you, the pressure is relentless. The damage could become permanent. You are floating in an endless black void, and your own body is slowly making you blind to it. Meanwhile, the wasting of your body deepens. After several years, your legs would be little more than skin and bone. The powerful muscles of your core and back would have wasted away to such an extent that you would settle into a permanent, semi-fetal, neutral body posture. To straighten your back would require a conscious effort. If you were suddenly returned to Earth, you would be unable to stand. Your skeleton would be in an even more perilous state. After 3 years, you might have lost over a third of the bone density in your hips and spine. You would have the skeleton of an advanced stage osteoporosis patient. A simple, clumsy movement could be enough to cause a fracture, and a fracture in this state would be a catastrophe, as the bone-building process is all but shut down. And what of your heart? The central engine of your body has now been deconditioned for years, becoming a smaller, less powerful muscle. Its ability to respond to any sudden stress would be critically low. For you, any event that demanded a sudden increase in heart rate, a moment of panic, a muscle spasm, could overwhelm the weakened cardiac muscle, possibly triggering a fatal arrhythmia. After multiple years adrift, you are a collection of strange new adaptations. Your eyes are deforming, your muscles have wasted, your bones are a fragile framework, and your heart has forgotten what it means to work hard. You have become a perfect specimen of decay, a living reminder of the body's absolute dependence on the force you have lost forever. The final stage, the psychological collapse. The physical disintegration of your body is a quiet, creeping process. But perhaps the ultimate journey unfolds not in your bones or muscles, but in the vast, lonely expanse of your mind. While your body is being reshaped by the absence of gravity, your consciousness is being reshaped by the absence of everything else. You are falling through a perfect void. This means more than darkness, it means a total absence of sensory input. No sound, no touch, no scent. No up or down. No day or night to mark the passage of time. Your own internal body clock, unmoored from any external cue, would drift aimlessly. This is a state of sensory deprivation and isolation more absolute than anything imaginable. The psychological effects of long-term isolation, even in less extreme cases, are well documented: anxiety, paranoia, hallucinations, and a decline in cognitive function. For you, these effects would be amplified to an unimaginable degree. For a while, your mind might fight back, creating daydreams or replaying memories. But over the years, without any new information to process or problems to solve, the brain itself would begin to change. What's so fascinating about the human mind is that it's a problem-solving machine, shaped by survival. Take away the problems, and what happens? The line between thought and dream would blur. You might begin to see things in the darkness and hear voices in the silence. This mental journey is connected to the failure of your own body. Your sense of self is deeply intertwined with your physical presence. Proprioception, the sense of where your limbs are in space, would become unreliable. You would feel disconnected from your own body, an untethered consciousness in a floating vessel that no longer feels like your own. Existence becomes purely passive. Over years, this would lead not just to a departure from reality, but to a form of cognitive change. The intricate personality, memories, and thoughts that make you would slowly unravel, worn away by the endless, featureless, silent eternity. You would become a ghost in your own dying machine. Conclusion. The quiet end. After a decade, or perhaps two, what is left? The person is gone, their consciousness dissolved by isolation and sensory starvation. What remains is a biological curiosity, a living reminder of the power of gravity, not unlike the strange creatures preserved in stone. The body is a fragile shell. The skeleton, having lost perhaps half its mineral density, is as brittle as glass. The muscles are thin, fibrous bands. The heart is a weak pump, beating feebly. The immune system, also known to be compromised by spaceflight, would be ill-equipped to handle even a minor infection. The end, when it comes, is not a dramatic event. It's a quiet, systemic whisper. It could be a spontaneous fracture, a minor infection, or a simple cardiac arrhythmia. A heart on Earth would correct this instantly. But this heart is too weak, too detached from the demands of a physical world. It cannot recover. The flutter turns to a quiver, and then, silence. In the end, falling forever isn't a dramatic plunge. It is a slow, methodical erasure. It is a testament to a fundamental truth. The human body is a relationship, a dynamic conversation with the force of gravity. We are shaped by the struggle against it. And without that constant battle, the body doesn't find freedom. It finds obsolescence. It becomes something quietly strange, a reminder that for life, normal was never the plan. Spaghettification. The most brutal death in the universe. Gravity is a force we feel every moment, but rarely consider its true potential. In most of the universe, it's a gentle guide, holding worlds in orbit and stars together. But in some places, it becomes something else entirely, a force of absolute deconstruction. At the edge of a black hole, an object, or an explorer unlucky enough to get too close, will face one of the most bizarre and violent ends in the cosmos. A process with a deceptively simple name, spaghettification. What is it that draws us to these places? From a safe distance, a black hole is an object of profound and terrifying beauty. A perfect circle of absolute blackness against the stars, surrounded by the chaotic, brilliant swirl of an accretion disk. That ring of superheated gas and dust shines with incredible energy, but the center is a void. It is a place where gravity has become a monster. A black hole is what remains when a massive star exhausts its fuel and collapses under its own weight. All of that mass gets crushed into a space so impossibly small that the result is an object with a gravitational field so intense that nothing can escape, not even light. The idea itself isn't entirely new. Thinkers in the 18th century imagined objects so massive that light couldn't get away. But what makes a black hole so dangerous isn't its mere existence. If our sun were replaced by a black hole of the exact same mass, the planets would continue to orbit just as they do now. The danger is proximity. To experience its true nature, you have to get very, very close. As an object gets closer, the first truly alien phenomenon it would witness is the warping of light. A black hole's immense gravity bends the fabric of spacetime itself, and light has to follow these curves in an effect called gravitational lensing. The light from stars behind the black hole is smeared and contorted into ghostly arcs. In a perfect alignment, light from a single star can form a complete circle surrounding the blackness, a celestial halo known as an Einstein ring. Closer still is an even more bizarre region, the photon sphere. This is a place where gravity is so strong that photons, particles of light, are trapped in orbit. Light here can loop around the black hole multiple times. Theoretically, an observer here could see the back of their own head as the light from it orbits the black hole and arrives in front of them. But these orbits are balanced on a knife's edge. The slightest nudge sends the photons either into the black hole or flying off into space. But perhaps the most profound distortion isn't of light but of time itself. General relativity tells us that strong gravity slows down time. For a distant observer watching an object fall in, it would appear to slow down, its light becoming redder and dimmer, until it seems to freeze at the edge for an eternity. For the object itself, however, time flows normally. Looking back out, it would see the future of the universe speeding up in a frantic, silent ballet of cosmic evolution. This brings us to the most famous part of a black hole, the event horizon. This is the boundary in space-time beyond which events can no longer affect an outside observer. It's the definitive point of no return. What would an explorer feel crossing this momentous threshold? The answer, perplexingly, is nothing. The event horizon isn't a physical surface. It is a purely mathematical line drawn in space-time. From a first-person perspective, there's no jolt, no flash. One moment, escape is difficult, the next, it's impossible. This is because the geometry of spacetime has warped so much that all possible paths now lead in only one direction, inward. Now, this strangely peaceful crossing is a feature of supermassive black holes, the kind with masses millions or billions of times that of our Sun. Their event horizons are so large that the curvature of spacetime at the edge is gentle. But for a smaller, stellar mass black hole, the story is very different. The tidal forces, the very forces that cause spaghettification, become extreme well before the event horizon is even reached. Inside, the direction toward the center is no longer just a direction in space. In a very real sense, it has become the future. Just as we cannot stop moving into our own future, an object inside a black hole cannot stop moving toward its center. The process that happens next has a whimsically terrifying name, famously popularized by Stephen Hawking in his book A Brief History of Time *, spaghettification. It's the ultimate expression of tidal forces. We see a gentle version of this every day. The moon's gravity pulls more strongly on the side of the Earth facing it, which causes the oceans to bulge and creates our tides. Near a stellar mass black hole, this effect is anything but gentle. The difference in gravitational pull between an object's head and feet grows exponentially. It would start as a stretching sensation, but would quickly overwhelm any material's structural integrity. The bones would be pulled apart at the joints. Simultaneously, another force is at work. While the object is stretched vertically, it's also compressed horizontally. Every part of it is being pulled toward the single point of the singularity, so it's squeezed from the sides, extruded like toothpaste from a tube. The process doesn't stop with the body. The tidal forces continue to intensify, tearing apart the very molecules that make up its tissues. The chemical bonds dissolve, and complex matter is reduced to a flow of individual atoms. Even the atoms themselves cannot survive. Eventually, electrons are stripped from their nuclei. What was once a complex object is now a river of dissociated subatomic particles, protons, neutrons, and electrons, plunging into the abyss. This is not merely destruction. It is a complete and utter deconstruction, reducing an organized structure back to its fundamental, unrecognizable parts. So what happens to this stream of particles? The answer lies at the heart of the black hole, in a place that challenges our current understanding of physics, the singularity. General relativity predicts that at the center of a simple, non-rotating black hole, all the mass is crushed into a point of zero volume and infinite density. But what is a singularity? The honest answer is, we don't know. The concept of infinite density is a sign that our theories are incomplete. It's the place where general relativity, our theory of the very large, collides with quantum mechanics, our theory of the very small, and the two refuse to agree. The laws of physics as we write them simply break down. Some theories suggest it might not be a point at all, but something like a Planck star, an object of incredible but finite density. For now, these are ideas on the frontier of physics. The singularity remains a point beyond which we cannot make verifiable predictions. The matter that falls in becomes part of a question mark at the very center of the cosmos. The journey of an object from our familiar universe into a stream of fundamental particles illustrates the awesome and terrifying power of gravity. We began by watching stars warp and time slow down. We crossed the invisible threshold of the event horizon, where the rules of reality are twisted. And finally, we saw how matter is systematically disassembled by tidal forces. Black holes are more than just cosmic monsters, they are the ultimate laboratories. They push the laws of physics to their absolute breaking point, revealing both the power of our theories and the vast gaps in our knowledge. They are a humbling reminder that the gentle force that anchors us to our world can, in the right circumstances, become the most powerful and destructive force in the entire universe. A testament to the sheer scale and power of the cosmos we are only just beginning to explore. The speed limit where falling stops. There is a law etched into the physics of our atmosphere, a boundary that governs every object in motion. It is a speed limit not on a road, but in the open air itself. For any object in freefall, this limit is the point where the entire nature of its descent is transformed. Hitting it means the violent acceleration of falling stops, replaced by a constant, controlled velocity. This is not a metaphor. It is a point of equilibrium where gravity's relentless pull is met by an equal and opposite force. Understanding this phenomenon, terminal velocity, changes our perception of what it means to fall. It is a principle that shapes everything from the character of a rain shower to the survival of an animal and the return of a spacecraft from orbit. The plunge, gravity's unbroken promise. To understand this speed limit, we must first consider the force that makes it necessary: gravity. In the first moments of a fall, gravity is the dominant actor. Near the Earth's surface, it imparts a constant acceleration of 9.8 meters per second for every second of descent. After 1 second, an object is moving at nearly 22 miles per hour. After 2, 44 miles per hour. After 3, 66. In a vacuum, where no other forces are present, this acceleration would continue indefinitely. This is gravity's essential promise. Unopposed, it will make an object move faster and faster, without limit. For nearly 2,000 years, scientific thought, inherited from Aristotle, held that heavier objects fall faster than lighter ones. It was an intuitive idea: a rock falls faster than a leaf. Aristotle reasoned that an object's speed was proportional to its weight, that a heavier object had a greater internal impetus to return to the center of the Earth. It was a logical framework, and it was incorrect. The idea was challenged by Galileo Galilei. Through a now famous thought experiment, he exposed a logical contradiction. Imagine a heavy cannonball and a light one. According to Aristotle, the heavy one falls faster. If you tie them together, does the lighter ball act as a drag, slowing the heavy one down? Or do they form a single, even heavier object that should fall faster than either one alone? The premise leads to a paradox. Galileo's resolution was radical. The initial assumption must be wrong. In a vacuum, all objects must fall at the same rate. This established gravity as a democratic force, the engine of the fall. But our world is not a vacuum. We are surrounded by an ocean of air, and within this medium, a second, opposing force is born. The invisible wall, the rise of a hidden force. An object falling through the atmosphere is moving through a fluid. Air is a substance with mass and density, a sea of nitrogen, oxygen, and other molecules. When an object moves through it, the air pushes back. This force is known as air resistance or drag. Unlike gravity, drag is not a constant force. It is dynamic, and its strength is determined primarily by speed. For most objects at high speeds, the drag force is proportional to the square of the velocity. Doubling your speed quadruples the air resistance. Tripling your speed increases it ninefold. This exponential relationship is why, in just a few seconds, air resistance can grow from a negligible influence to a powerful physical barrier. This force is described by the drag equation: F_d equals frac 1, 2, rho v squared AC_d. Each term represents a critical factor in this opposition to gravity. Rho, rho, is the density of the fluid. Air at sea level is far denser than the thin atmosphere at 40,000 feet. The thicker the medium, the stronger the resistance. V squared velocity squared, is the engine of drag. It is the variable that links the speed of the fall directly and exponentially to the resistance it creates. A** is the object's cross-sectional area, the size of its silhouette as it meets the air. A person falling in a spread eagle position presents a large area, creating significant drag. If they orient into a head-down dive, their area shrinks, and so does the resistance. Finally, C_d* is the drag coefficient, a measure of an object's aerodynamic shape. A brick is not streamlined. It has a high drag coefficient because air tumbles chaotically behind it. A teardrop shape, by contrast, is streamlined. It has a low drag coefficient, allowing air to flow smoothly over its surface with far less resistance. Together, these four factors, density, velocity, area, and shape, determine the strength of the opposing force. The story of a fall is the battle between constant gravity pulling down and variable drag pushing up. The equilibrium, where the battle ends. In the first seconds of a fall, the force of gravity is far greater than the force of drag. The net force is downward, and the object accelerates rapidly. But as velocity increases, the v² term ensures that the upward force of drag grows exponentially. The initial feeling of acceleration gives way to a sense of being cushioned by the building air pressure. The net downward force shrinks as the upward drag force grows to meet it. Then, a critical threshold is crossed. For a typical skydiver, this happens after about 10 to 12 seconds. Their velocity becomes so great that the upward force of air resistance becomes precisely equal to the downward force of gravity. The two opposing forces are in perfect balance. According to Newton's first law, an object's velocity will not change unless it is acted upon by a net, unbalanced force. At this moment, the net force on the skydiver is zero. Acceleration ceases. This is terminal velocity. The physics of the fall has fundamentally changed. The object stops gaining speed. If it reaches this equilibrium at 120 miles per hour, it will continue to fall at 120 miles per hour. The sensation is no longer one of being pulled down, but of being suspended in a powerful, upward rushing column of wind. This is the speed limit of the sky. It is the point where gravity's promise of infinite acceleration is broken by the physical reality of our atmosphere. For a typical skydiver in a belly-to-earth position, this speed is around 120 miles per hour, about 55 meters per second. The height of a fall determines if and for how long an object travels at terminal velocity, but it does not change the value of that velocity. Manipulating the limit, the variables of velocity. Terminal velocity is not a universal constant. It is a dynamic limit unique to each object and situation. The physics that defines it also provides the instructions for how to change it. The equation for terminal velocity is derived at the moment drag force equals gravitational force, F_d equals F_g, and when solved for velocity, it gives us this. V_t equals sqrt, frac 2 milligrams, rho ac_d. Every variable in this formula is a lever that can be pulled to alter the outcome. Manipulating area, **. This is the primary tool for a skydiver. Having reached a stable terminal velocity of 120 miles per hour, a skydiver can transition into a streamlined, head-down dive. Their mass, the air density, and their drag coefficient remain roughly the same, but their cross-sectional area, A, decreases dramatically. Instantly, the upward drag force becomes smaller than the downward force of gravity. The balance is broken, and acceleration begins again. The skydiver's speed increases until the v² term grows large enough to compensate for the smaller area, establishing a new, higher terminal velocity. Competitive speed skydivers can achieve speeds over 300 miles per hour, with the current record held by Kyle Lobpries at over 318 miles per hour. By manipulating their body's area, they control their rate of descent. Manipulating mass, m***. This brings us back to Galileo. On Earth, a bowling ball falls much faster than a feather. The reason is not a greater impetus, but the relationship between mass, area, and drag. The bowling ball has a large mass, m, and a relatively small, streamlined profile, small a and c_d. It must achieve a very high velocity for the drag force to grow strong enough to equal its significant weight. The feather has a tiny mass and a large surface area for its weight. It needs to generate only a minuscule drag force to find equilibrium, a balance it strikes at just a few miles per hour. In the real world, heavier, denser objects often do fall faster, because their mass requires a higher speed before air resistance can counteract their weight. Manipulating shape, C_d, and density, rho, asterisk. The effect of shape is perfectly illustrated by a golf ball. Counterintuitively, a dimpled golf ball has a higher terminal velocity than a perfectly smooth sphere of the same size and mass. The dimples create a thin, turbulent layer of air that clings to the ball's surface, reducing the drag-inducing weight behind it. This lowers its drag coefficient, c_d, and allows it to travel faster. The most extreme example of these principles involves the variable of air density, rho. On October 24, 2014, Alan Eustace jumped from an altitude of over 135,000 feet. In the near vacuum of the stratosphere, air density was practically zero. With almost no drag to oppose it, he accelerated at nearly the full 9.8 meters per square second, reaching a top speed of 822 miles per hour, Mach 1.22. He broke the sound barrier. But this was not his impact speed. As he plummeted into the thicker, denser air of the lower atmosphere, the rho term in the drag equation grew. The force of air resistance became immense, far greater than the force of gravity, and it began to slow him down. He was an object moving faster than his terminal velocity for that denser air, so he decelerated. The atmosphere forced him to settle down to a normal, subsonic terminal velocity, at which point he could safely deploy his parachute. The limit in our world, from raindrops to spacecraft. Terminal velocity is not an abstract concept. It is a feature of physics that silently shapes our environment. A raindrop forms thousands of feet in the atmosphere. If it fell in a vacuum, it would strike the ground at hundreds of miles per hour, giving a simple rain shower the destructive force of tiny projectiles. Instead, a raindrop quickly reaches its terminal velocity of about 20 miles per hour and coasts the rest of the way down at this survivable speed. The same principle applies to biology, as explained by the square-cube law. As an organism scales down, its mass, related to volume, a cubed dimension, decreases far more rapidly than its surface area, a squared dimension. For very small animals, their surface area is enormous relative to their mass. An ant has a terminal velocity of only a few miles per hour. It can fall from any height and walk away unharmed. The biologist J.B.S. Haldane noted this scale effect. You can drop a mouse down a 1,000-yard mine shaft. And, on arriving at the bottom, it gets a slight shock and walks away. A rat is killed, a man is broken, a horse splashes. This is a direct consequence of their different masses, areas, and resulting terminal velocities. Perhaps the highest stakes application of this principle is in space exploration. A returning spacecraft enters the atmosphere at orbital velocity, around 17,500 miles per hour. It cannot carry enough fuel to brake with rockets. Instead, engineers use the Earth's atmosphere as a colossal brake. The capsule enters at a shallow angle, and the immense drag converts its kinetic energy into heat, requiring a massive heat shield. This entire process of aerobraking is designed to bleed off thousands of miles per hour of speed, allowing the capsule to slow to a subsonic terminal velocity where it is finally safe to deploy parachutes. Conclusion: the controlled descent. Let us return to the skydiver, coasting at a terminal velocity of 120 miles per hour. This is not a safe landing speed. By pulling the ripcord, the skydiver executes a final, radical manipulation of the physics of their fall. A parachute is a tool designed to monumentally increase both area, A, and drag coefficient, c_d. In an instant, the upward force of drag becomes overwhelmingly greater than the downward force of gravity. The balance is shattered, resulting in a powerful deceleration. The skydiver's velocity plummets until a new equilibrium is found. A new, much slower terminal velocity of around 15 miles per hour is established, permitting a safe landing. The entire journey is a demonstration of these physical laws. It begins with the pure acceleration of gravity, is met by the rising opposition of drag, finds a temporary peace at one terminal velocity, and concludes with a deliberate intervention to create a new, survivable one. From the silent drift of a snowflake to the fiery re-entry of a meteor, this speed limit is a fundamental boundary. It shows that even in a chaotic fall, there are laws that provide balance, structure, and for those who understand them, a means of control. The universe's ultimate one-way trip. Imagine you're an explorer, drifting through the silent, velvet black of deep space. Your mission is over. You're heading home. Through your viewport, the sea of distant stars is a familiar, comforting sight. But then, you see something wrong. A patch of sky that's too perfect, too black. It's a circle of pure nothing, punched right out of the cosmos, snuffing out the stars behind it. You're not looking at an object. You're looking at the asterisk absence of them. An abyss. Before your brain can even catch up, you feel it. A gentle, but insistent pull. A current in the river of spacetime, tugging your ship. Your alarms are silent, your course seems stable. And yet, the pull is real. You've just stumbled, by pure cosmic luck, onto the universe's ultimate one-way trip. You are on a path to a place where time and space break down, where the laws of physics get torn to shreds. You are falling toward a black hole. What happens next isn't a story of flashy explosions or frantic escapes. It's a story of physics at its most extreme. It's a journey that literally splits reality in two, a fall that no one can ever watch. You're about to cross the event horizon, the point of no return. But what does that actually mean? What would you feel? What would you see? And where does your story really end? The lure of the abyss, the setup. To understand your journey, you first have to understand your destination. This perfect circle of darkness isn't a hole in the normal sense. It's the exact opposite, an unbelievable amount of stuff, of mass, crushed into a space so small it's basically zero. Picture a star, many times bigger than our sun, squeezed down into a volume smaller than an atom. The best way to imagine what this does to the universe is the classic analogy. Think of spacetime as a huge, stretchy rubber sheet. A planet like Earth is a marble on that sheet. It makes a little dimple. That dimple is gravity, it's what keeps the moon circling around us. A star is a bowling ball, making a much deeper well. But a black hole, that's something else. It's like a lead weight so heavy it has punched clean through the sheet, creating a bottomless pit. A well so deep it doesn't just warp space, it warps time itself. These cosmic monsters are born from the death of giants. Imagine a star, a colossal fusion reactor at least 20, maybe 30 times more massive than our sun. For millions of years, it rages, the outward blast of its nuclear furnace perfectly balancing the inward crush of its own gravity. But that balance can't last. Eventually, the star runs out of fuel. The furnace goes out, and in an instant, gravity wins. It wins disastrously. The star's core collapses in on itself in less than a second. The outer layers are blown away in a supernova, an explosion so violent it can outshine its entire galaxy. But for the core, the crush doesn't stop. Gravity is now so totally in charge that it overpowers every other force in nature. Atoms are smashed into exotic new forms of matter, and then smashed again. The collapse just keeps going, unstoppable, until all of that mass is packed into a single point of zero volume and infinite density. A singularity. The black hole is born. As your ship gets pulled closer, you realize the first danger isn't the black hole itself, but the chaos around it. Let's pretend for our trip you found a uniquely quiet one, all on its own. Most aren't like that. They're surrounded by an accretion disk, a terrifying, screaming vortex of gas, dust, and the shredded guts of stars that got too close. This stuff spirals inward, accelerating to nearly the speed of light. The friction heats it to millions of degrees, making it one of the brightest sources of X-rays in the sky. Flying through that would be like flying into a star. You'd be vaporized long before you got anywhere near the main event. So, let's assume you've found a clean path, avoiding that cosmic blender. You're now nearing a zone of pure weirdness called the photon sphere. Here, outside the black hole's final border, gravity is so powerful that particles of light, photons, get trapped in orbit. They don't fall in, not yet, but they can't leave either. They just circle the black hole forever. From your viewport, the effect would be unreal. Light from distant galaxies bends around the black hole, creating warped, funhouse mirror images. But even weirder, light from the back of your own ship could get caught in the sphere, do a lap, and then arrive at your viewport from the front. In this bizarre place, if you turned your head just so, you could theoretically see the back of your own head. It's a dizzying preview of what's to come. But the real boundary is just ahead. The edge of forever, the point of no return. You're approaching the event horizon. This is the most famous part of a black hole, and maybe the most misunderstood. It's not a surface. There's no wall to hit, no membrane to break. The event horizon is just a line, an invisible boundary drawn in spacetime itself. It's defined by one terrifying fact. This is the point where gravity gets so strong that to escape, you'd have to go faster than the speed of light. Think about launching a rocket from Earth. You need to hit about 25,000 miles per hour to break free from its gravity. On a bigger planet, you'd need to go faster. Now imagine an object so dense that the escape velocity is more than 670 million miles per hour, faster than light itself. Since nothing can go faster than light, that means once you cross this line, you're not coming back. Not you, not your ship, not even a beam of light. It is, literally, the point of no return. And right here, your journey splits into two different stories, told from two different points of view. Both are true. Both completely contradict each other. First, let's see it from the eyes of your friend, watching safely from a mothership far away. As you get closer to the horizon, they watch your ship through a telescope. They see the clock on the outside of your ship start to tick slower and slower and slower. This is gravitational time dilation, a key piece of Einstein's theory of general relativity. The stronger the gravity, the slower time flows for you compared to someone outside. As you get closer, the effect gets wild. From your friend's perspective, your ship seems to grind to a halt, taking forever to cross those last few feet. The light from your ship stretches into longer, redder wavelengths, gravitational redshift. Your ship's bright white hull shifts to orange, then deep red, then fades away into infrared, and finally, nothing. To your friend, you are frozen in time at the edge of the event horizon. A ghostly red image smeared across the boundary for all eternity. They never see you cross. From their perspective, your journey just stops. But for you, inside your ship, everything feels completely normal. Your clock ticks on just fine. You don't feel a bump, a jolt, or any sign that you've just crossed a cosmic Rubicon. In fact, if you're falling into a really big, supermassive black hole, the kind with millions or billions of suns worth of mass, crossing the event horizon is shockingly uneventful. You just float right over the invisible line, totally unaware that you just sealed your fate. If you looked back at the mothership, though, you'd see the asterisk real show. As you cross the horizon and fall deeper, time dilation works in reverse. Looking out, you would see the rest of the universe in fast forward. You'd see your friend's ship age and fly away. You'd see distant stars evolve, burn out, and die in seconds. You'd see entire galaxies spin and collide. In the brief moments it takes you to fall toward the center, you witness eons of cosmic history flash before your eyes. You see the universe itself grow old. It's the greatest show in the cosmos, and you're the only one in the audience. You've left our shared reality behind. If the idea of watching the universe's entire future flash before your eyes is blowing your mind, you're starting to get it. This journey into the unknown is what science is all about. If you want to explore more mind-bending ideas like this, go ahead and subscribe to our channel. We ask these kinds of cosmic questions every week, pushing the limits of what we know. There's a lot more of this one-way trip to go, so hit that subscribe button, and let's keep falling. The long descent, the experience of falling. You're inside the event horizon now. The outside universe is gone, having fast-forwarded to its own end from your perspective. Ahead, there's only darkness. And the rules have fundamentally changed. Before you crossed the line, you could fire your engines and go anywhere in space. Up, down, left, right, your choice. Not anymore. Inside the horizon, space-time is so warped that space and time have sort of switched roles. The direction, inward, toward the singularity, isn't a direction in space anymore. It is the future. Every possible path you can take, no matter which way you turn or how hard you fire your engines, ends at the center. Trying to fly away from the singularity is now like trying to travel back to yesterday. It's impossible. The singularity isn't a place you're going to. It's an appointment in time you are destined to keep. Your fall is now as certain as tomorrow. For our trip, we picked a supermassive black hole. That was a smart choice if you wanted to survive for more than a nanosecond. The reason comes down to tidal forces, and a process with a wonderfully terrifying name, spaghettification. Tidal forces are just a side effect of gravity. On Earth, the moon pulls a little harder on the side of the Earth facing it than the side facing away. This difference stretches the planet and creates our ocean tides. Now, imagine that effect cranked up to 11 by a black hole. If you fell into a small, stellar mass black hole, the tidal forces would be insane, even outside the event horizon. The pull on your feet would be trillions of times stronger than the pull on your head. That difference would stretch you like a piece of spaghetti. You'd be pulled apart, atom by atom, into a thin stream of plasma before you even got to the main event. A very short, very messy trip. But a supermassive black hole is different. Its event horizon is huge, millions to billions of kilometers across. Because it's so big, the curve of spacetime at the edge is actually much gentler. The difference in gravity between your head and your feet would be so small you wouldn't even feel it. That's why you could float right across the horizon, no problem. You could be inside for minutes, maybe even hours in the biggest ones, just drifting in the quiet dark before things get ugly. But they will get ugly. As you fall, the gravitational slope gets steeper and steeper. The gentle stretching begins. At first, it might just feel like you're getting taller. But the force grows exponentially. Your ship starts to groan as the metal at its front is pulled harder than the metal at its back. Stress fractures spiderweb across the hull, and it begins to tear apart. You're next. You're stretched longer and thinner. Your bones snap. Your tissues tear. The very molecules of your body are ripped from each other. Eventually, even your atoms are dismantled, their electrons stripped away from their nuclei. You, your ship, and everything you brought with you are no longer anything but a thin, glowing stream of fundamental particles, plunging toward the end of everything. The end of physics, the singularity. Your one-way trip is reaching its final stop. That stream of particles that used to be you is now approaching the heart of the black hole, the singularity. According to Einstein's general relativity, this is it. The end of the line. A point with zero size and infinite density. All the mass of that dead star, and every bit of matter that fell in since, is crushed into a region that has no dimensions. Here, space-time curvature becomes infinite. Gravity becomes infinitely strong. The very ideas of space and time just dissolve. The laws of physics, as we know them, break down. When we try to use our equations to describe a singularity, they just spit back infinity. And in physics, infinity isn't an answer, it's a warning sign. It's the universe telling us our theory is broken. General relativity is a masterpiece for describing gravity on a large scale, but it doesn't know how to talk to quantum mechanics, the science of the very small. At the heart of a black hole, where you have unimaginable mass in an impossibly tiny space. Both theories have to work, but they refuse to play nice. So what really happens at the center? We don't know. It's one of the biggest unsolved mysteries in all of science. To get the real answer, we need a theory of quantum gravity, a single framework that can finally unite these two great pillars of physics. Of course, physicists have some wild ideas. String theory suggests the singularity isn't a point, but maybe a vibrating, fuzzy ball of energy. Loop quantum gravity proposes that spacetime is made of tiny, indivisible chunks. You wouldn't be crushed to an infinitesimal point, but you'd hit the pixel of reality. At that point, gravity might even flip and become repulsive, causing all that matter to bounce and maybe erupt as a new universe. Could a black hole be a gateway to another cosmos? It's a mind-bending possibility, but for now, it's pure speculation. Your personal journey ends right here, at the edge of known physics. The stream of particles that was you merges with whatever is at the center. But your story isn't quite over. Because by falling in, you've just created a huge, baffling puzzle for the rest of us. A ghost in the cosmic machine. The ghost in the machine, the aftermath and the paradox. You're gone. But what about the asterisk information that made you? The unique arrangement of your atoms, the memories in your brain, the blueprint of your existence. It's all now locked behind the event horizon, seemingly erased from the universe. General relativity is clear. Nothing gets out. But that simple statement creates a massive headache when it runs into quantum mechanics. See, a core rule of quantum mechanics is that information can never be destroyed. It can be scrambled or rearranged, but it's never truly lost. If you burn a book, all the information in the ink and paper isn't gone. In theory, if you could collect every single particle of smoke, ash, and heat, you could piece the original book back together. Information is always conserved. A black hole seems to break this fundamental rule. Then, in the 1970s, Stephen Hawking discovered something startling. He found that black holes aren't completely black. They glow, ever so faintly, with what we now call Hawking radiation. This happens because of quantum weirdness right at the edge of the event horizon, where pairs of virtual particles can pop into existence. Normally they just cancel each other out, but if one falls in and the other escapes, the escaping particle becomes real and carries away a tiny speck of the black hole's energy. Over trillions upon trillions of years, this slow leak of radiation will cause the black hole to completely evaporate, disappearing in a final flash of gamma rays. And here's the paradox. Hawking's original math showed that this radiation is random. It contains no information about what fell in. So, when the black hole is gone, what happened to the information that made you? Is it destroyed forever, breaking one of the most basic laws of physics? This is the black hole information paradox. For decades, this puzzle has stumped physicists. Which theory was wrong, general relativity or quantum mechanics? But recently, breakthroughs have pointed toward a stunning solution. The information does get out. One of the leading ideas is the holographic principle. It suggests that all the information about what falls into a black hole isn't actually inside it, but is encoded on the 2D surface of the event horizon, like a cosmic hologram. As the black hole evaporates, that information is subtly imprinted onto the outgoing Hawking radiation. Recent, incredibly complex calculations involving things called replica wormholes have even shown mathematically how this could work, suggesting there are tiny quantum connections between the black hole's interior and the radiation far outside. So, the information that was you isn't destroyed. It's scrambled and encoded into the faint glow of the evaporating black hole, and then radiated back out across the cosmos over eons. Your story is still there, just written in a code so complex it would be virtually impossible to ever read. Your one-way trip began with a simple fall into the dark. It took you across a boundary that splits our reality in two, to a place where you saw the universe die in the blink of an eye. Your journey continued into a region where space becomes your destiny, ending in an unavoidable crush at a point where our understanding of physics simply ends. You, the traveler, are gone, torn apart and merged with the singularity. But the essence of you, the information that made you you, lives on. Not lost in the abyss, but painted onto the edge of spacetime and then slowly, painstakingly, released back into the cosmos. Your fall was an event no one could ever witness, but your story becomes a faint, quantum ghost, echoing through the ages. Your journey ends where physics breaks. But the question of your existence, the information that made you, still echoes. What do you think really happens to a story when it falls into a black hole? Let us know your theory in the comments. And for more journeys to the edge of what's possible, make sure you're subscribed. Gravity wrote the first and last page of the universe. There is a process so fundamental you feel it with every step you take. It's a quiet, constant presence, the reason things fall. But this same familiar process also operates on the grandest scale imaginable, shaping the movement of galaxies across billions of light years. That process is gravity. It's the underlying rule that has guided the formation of almost everything we see, from planets and stars to the largest cosmic structures. It has been at work for 13.8 billion years, and its influence stretches across the entire history of the universe. Welcome to the Sleepy Scientist. This single principle was present at the universe's explosive beginning, and its influence is already shaping what seems to be its final state. The whole existence of the cosmos, from its first moments of light to its last fading energy, seems to follow from its persistent effects. So how does this work? How can one set of rules explain both the rapid formation of everything we know, and its potential, eventual disappearance into cold and darkness? To understand this, we need to look back to the very beginning, to a moment before time as we know it, where the conditions for our entire reality were contained in an unimaginable state. Act 1. The first page, the Big Bang. Before the beginning, there was no before. Space, time, and matter as we understand them didn't exist. All the energy of the cosmos was contained in a point of extreme density and temperature, a state known as a singularity. This is where our current models of physics, even Einstein's general relativity, can no longer give us answers. It's a boundary to our knowledge, a point of pure potential that our science has yet to cross. Then, 13.8 billion years ago, the expansion began. This wasn't an explosion in space, but a rapid expansion of space itself. In the first tiny fraction of a second, the universe underwent a phase of incredible growth called cosmic inflation. Physicists think this was driven by the energy of a false vacuum, a state that produced a powerful negative pressure, acting as a repulsive force that pushed space apart. The universe swelled from a subatomic size to cosmic proportions in less than a trillionth of a second, smoothing out the fabric of spacetime into the vast, uniform canvas we see today. But this state didn't last. When inflation ended, the universe was left as a fantastically hot, dense soup of fundamental particles and energy. And in this primordial plasma, gravity began to assert its familiar, attractive nature. In the immense density of the early universe, it was a powerful force, pulling everything inward, working against the expansion. For the first 380,000 years, the universe was an opaque fog. The heat and density were so extreme that light photons couldn't travel far without scattering off free-roaming electrons. But as space continued to expand, it also cooled. Gravity was playing a long game, locked in a tug-of-war with the universe's outward momentum, acting as a brake on the expansion. As the cosmos cooled, a critical transition occurred. Protons and electrons could finally combine to form the first stable atoms, mostly hydrogen and helium. At this moment, the universe became transparent. The light that had been trapped for millennia was suddenly released. We can still see this light today as the cosmic microwave background radiation. It's like a fossil from that moment, a detailed snapshot of the universe when it was just 380,000 years old, with the faint afterglow of creation still visible. Imprinted on this ancient light are the seeds of all future structure. There are tiny, almost imperceptible variations in temperature and density that were stretched to enormous scales by inflation. These minuscule areas of slightly higher density became the starting points for everything that would come next. For gravity, that small imperfection is everything. Its gentle, relentless pull would now begin to draw the surrounding gas toward these points. The stage was set. The universe was a vast, dark space filled with simple gases, and under the quiet influence of gravity, the next phase of cosmic history was about to begin. Act 2. The author at work, gravity's reign. After the Big Bang, the universe was vast, dark, and mostly uniform, filled with a thin haze of hydrogen and helium. But mostly is the key word. The story of the cosmos from this point forward is the story of gravity taking advantage of small imperfections. But gravity wasn't working alone. It had an invisible partner that makes up about 27% of the universe, dark matter. It doesn't interact with light, so we can't see it, but it does have mass, and therefore, it has gravity. Long before normal matter could clump together, gravity was pulling this dark matter into a vast, interconnected network of filaments. A colossal structure often called the cosmic web. Dark matter formed immense, invisible halos, and these halos became the gravitational centers, the construction sites where the visible universe would be built. Imagine these giant, invisible regions of mass, patiently waiting in the dark. Gravity began to pull the abundant hydrogen and helium gas toward them. For millions of years, gas streamed along the filaments of the cosmic web, funneling into the hearts of the dark matter halos. As the gas clouds grew, they became denser and denser. Inside these collapsing clouds, gravity's effects grew stronger. The pressure at the center caused the temperature to climb. After tens of millions of years of compression, the core of the densest clumps reached about 10 million degrees Celsius. At that point, a new process began, nuclear fusion. Hydrogen atoms were forced together so violently that they fused into helium, releasing an enormous amount of energy. This was the birth of the first stars. These weren't like our sun. Known as population 3 stars, they were giants, hundreds of times more massive, forged from the pure hydrogen and helium of the early universe. They were the first lights in the darkness, burning incredibly hot and living short, violent lives. The same force that ignited them also determined their end. The outward pressure from fusion in a star's core constantly pushes against the inward crush of its own gravity. For these massive first stars, the battle was brief. They exhausted their fuel in only a few million years. When the fuel ran out, the outward pressure stopped, and gravity won instantly. The core collapsed, triggering a massive explosion known as a supernova. These first supernovae were essential. They forged the first heavy elements, carbon, oxygen, iron, and blasted them out into space. This was how the universe created new materials for the next generation of stars. This cycle of birth, death, and enrichment repeated. The heavy elements seeded nearby gas clouds, and new stars formed from this enriched material. All the while, gravity was working on an even larger scale. The dark matter halos, now filled with stars and gas, began to pull on each other. Clusters of stars merged to form the first dwarf galaxies. Over billions of years, these small galaxies performed a slow gravitational dance, orbiting, colliding, and merging to become ever larger. This is how the grand spiral and elliptical galaxies we see today were assembled. Our own Milky Way is a product of this process, built from countless mergers over eons. It was during this era that our understanding of gravity itself had to change. For centuries, Isaac Newton's idea of gravity as a mysterious pulling force was the best model we had. But in 1915, Albert Einstein's theory of general relativity gave us a completely new way to look at it. Einstein realized that gravity isn't a force in the traditional sense, but a feature of the universe itself. He showed that space and time are woven into a single four-dimensional fabric, spacetime. And the presence of mass and energy curves this fabric. The classic analogy is a bowling ball on a trampoline. It creates a dip, and a marble rolled nearby follows that curve. The marble isn't being pulled, it's simply following the straightest possible line through a curved space. This is gravity. This new idea explained quirks in Mercury's orbit and predicted that starlight should bend around the Sun, an effect called gravitational lensing that we now use to map dark matter. It also made two other strange predictions: black holes and gravitational waves. Black holes are what's left when a truly massive star collapses under its own gravity so completely that nothing, not even light, can escape. They are the most extreme expression of mass-curving spacetime. For a century, gravitational waves were just a theoretical idea. Ripples in the fabric of spacetime created by violent events like two black holes colliding. But in 2015, the LIGO experiment detected these ripples for the first time. We could finally hear the echoes of these massive cosmic events, opening a new way to observe the universe. From the first atoms to the first stars and galaxies, gravity was the underlying process that sculpted a simple, uniform universe into the structured cosmos we see today. But a new factor was quietly emerging, one that would change the course of the universe's future. Act 3. The last page, the ultimate fate. For billions of years, the cosmic story seemed to be a simple contest between the outward momentum from the Big Bang and the inward pull of gravity. Since the universe's expansion was slowing, it looked like gravity was winning. This led to two likely possibilities for the future. A big crunch, where gravity would eventually reverse the expansion and pull everything back into a singularity, or a big freeze, where the expansion would slow down forever but never quite stop. Then, in the late 1990s, astronomers studying distant supernovae found something completely unexpected. Their data showed that the expansion of the universe was not slowing down. It was speeding up. This discovery changed cosmology. Something was counteracting gravity on the largest scales. Scientists call this unknown influence dark energy. It's now believed to make up about 68% of the universe's total mass energy, and it acts as a sort of repulsive force, pushing spacetime apart. Around 5 billion years ago, as our solar system was forming, the universe passed a tipping point. As it expanded, the density of matter and dark matter decreased, so gravity's influence on the cosmic scale weakened. Dark energy, however, seems to be a property of space itself. As more space is created, its total effect grows. It became the dominant force driving the universe's evolution. So what does this mean for the far future? The evidence points toward a scenario known as the Big Freeze, or heat death. It's not a sudden end, but a very, very slow fading into darkness over incomprehensible timescales. First, over the next 100 billion years or so, the accelerating expansion will carry all galaxies outside of our own local, gravitationally bound group beyond our cosmic horizon. They will be receding faster than light, so their light will never reach us again. The sky will become empty of other galaxies. Within our own lonely supergalaxy, Milkomeda, stars will continue to form for a while. But over trillions of years, the gas needed for starbirth will run out. The stars will begin to die. Sun-like stars will become white dwarfs, and more massive stars will have already left behind neutron stars and black holes. The last lights to go out will be the red dwarfs, which burn their fuel so slowly they can last for trillions of years. But eventually, they too will fade. By about 100 trillion years from now, the last star will likely have died. The universe will enter a degenerate era, populated by the dead remnants of stars. Over even longer timescales, gravitational interactions will cause these dead stars to either be ejected from the galaxy or spiral into the supermassive black hole at its center. Some theories even predict that protons themselves will eventually decay, causing these stellar remnants to evaporate into a sea of particles. All that will remain are black holes. For a time, they will be the last remaining complex objects. But even they are not permanent. Due to quantum effects, a process known as Hawking radiation causes black holes to slowly leak energy and evaporate. This process is incredibly slow. A supermassive black hole could take 10 to the power of 100 years to disappear. But eventually, in a final, faint pop of energy, the last black hole will be gone. What's left is the heat death. A universe expanded to an incredible size, almost perfectly empty and cold, with a temperature approaching absolute zero. All meaningful activity will have stopped. It is the logical endpoint of entropy, the final, quiet state of the system. Time itself may lose its meaning. There is another, more speculative possibility known as the Big Rip. In this idea, dark energy grows stronger over time, eventually becoming strong enough to tear apart galaxies, stars, planets, and finally, atoms themselves. While the Big Freeze is more consistent with current data, it's a reminder that our understanding of these forces is still evolving. The journey from that first moment to this potential end is a humbling one. It really reframes our own brief existence. The same fundamental rule that keeps us on the ground is what built the cosmos and will guide its final moments. What part of this cosmic timeline do you find the most interesting? Let us know your thoughts in the comments. Conclusion: from a state of near infinite density to a future of near perfect emptiness, the shape of the universe is guided by one fundamental process: gravity. It's the principle that allowed the simple, hot aftermath of the Big Bang to organize itself into the complex and beautiful cosmos we see. It gathered matter, lit the stars, and assembled galaxies. Every structure we observe is a result of its influence. But the expansion it worked against for billions of years eventually diluted its power on a cosmic scale, allowing dark energy to become the dominant influence. Now, gravity's role has shifted. It still holds galaxies and solar systems together, but it no longer controls the ultimate fate of the universe. It will guide the last stars to their end and gather their remnants into black holes. But as its final creations evaporate, its work will be done. The beginning was incredibly hot and bright. The end will likely be incredibly cold and dark. But everything in between, every star, every planet, and our own existence, is a result of this quiet, persistent, and inescapable process. So the next time you drop something, just for a second, you're not just seeing an object fall. You're seeing the same fundamental rule that shaped the beginning of the universe, and is still shaping its end.